4.6 billion years ago, there was no Earth beneath your feet. There was no Atlantic Ocean rolling against distant shores, no Pacific stretching blue beneath clouds, and no familiar moon hanging quietly above a nighttime horizon. There were no mountains, forests, rivers, or continents. There was not even a planet waiting patiently in darkness. Yet the ingredients were already there. Imagine standing beneath a clear night sky, long before anyone understood what those distant points of light truly were. The ground beneath you feels cool after sunset, somewhere beyond the firelight. Insects murmur through grass, while smoke carries the dry smell of burning wood into the darkness. You look upward. For most of human existence, that simple act was the beginning of cosmology. Before telescopes, equations, observatories, or spacecraft, people possessed two remarkably useful astronomical instruments. They had their eyes, and they had enough patience to notice when something happened again. The sky rewarded patience. The sun rose from roughly the same side of the horizon each morning. The moon changed shape according to a recognizable rhythm. Certain stars appeared during particular seasons, then disappeared for months before returning. Planets behaved more strangely. Unlike most stars, they wandered slowly across the celestial background. Occasionally, some seemed to stop and reverse direction before continuing onward. Without modern instruments, the sky did not look like an enormous universe filled with galaxies. It looked much closer, almost architectural, like a luminous ceiling surrounding the human world. And Earth seemed perfectly still. You could hardly blame anyone for reaching that conclusion. You feel no enormous planetary rotation beneath your feet. A stone dropped from your hand falls downward rather than being left behind by a rapidly moving world. Common experience suggested stability. Across many ancient societies, people therefore placed the human world near the center of their cosmic stories. The details differed enormously, but the instinct was understandable. Earth felt solid. The heavens moved. Long before written astronomy appeared, communities were already watching celestial cycles carefully enough to organize important parts of life around them. Seasonal changes mattered to hunters, farmers, travelers, and communities preparing for winter. The sky could become a calendar. You might notice that sunrise slowly shifts along the horizon throughout the year. You might learn that certain stars return before seasonal rains or changing temperatures. Such observations required no knowledge of gravity or orbital mechanics. They required memory, repetition, and generations willing to compare one year with another. Some prehistoric monuments appear aligned with important solar directions, although interpreting their exact purposes remains difficult. Archaeologists continue debating how much astronomical knowledge should be inferred from particular structures. That uncertainty matters. A stone, aligned with sunrise, might represent careful astronomy, ritual symbolism, practical calendrical knowledge, or several purposes woven together. Ancient people rarely separated religion, agriculture, navigation, and astronomy into the neat categories used today. Their sky was part of ordinary life. You can imagine the atmosphere around one of those early observations. Cold stone presses against your palm before dawn. Damp earth carries the smell of grass and smoke. Conversation becomes quiet. Then sunlight appears at a familiar place along the horizon. Nothing about that moment tells you Earth's age. Nothing tells you that the stone beside you contains atoms forged through processes older than the planet itself. Nothing reveals that Earth formed from material circling a young star billions of years earlier. Those discoveries would require an extraordinary detour through human history. Ancient Babylonian observers eventually created systematic records of celestial events, including planetary motions and eclipses. Egyptian observers connected celestial cycles with calendars, agriculture, religious practice, and the seasonal rhythms of the Nile. Greek thinkers later tried something different. They increasingly asked whether the heavens could be described through geometry and natural principles. Aristotle developed an influential picture of a spherical Earth positioned within an ordered cosmos. This was not merely a foolish guess awaiting correction. A stationary Earth surrounded by moving heavens agreed with much ordinary observation and could be incorporated into a sophisticated philosophical system. More importantly, geocentric models could make useful predictions. Yet alternatives appeared surprisingly early. Aristarchus proposed that Earth moved around the Sun many centuries before heliocentrism became widely accepted. His idea survived only imperfectly, and convincing observational evidence remained painfully difficult to obtain. The stars offered a problem. If Earth traveled through a vast orbit, nearby stars should appear to shift against more distant ones. Ancient instruments could not detect that tiny effect. One possible explanation was that Earth did not move. Another was stranger. Perhaps the stars were unimaginably distant. That second possibility required a cosmos vastly larger than everyday intuition suggested. Humanity would need many centuries before instruments became precise enough to demonstrate just how enormous those distances were. Hipparchus measured celestial positions with impressive care and produced influential astronomical work. Ptolemy later constructed a mathematical geocentric system capable of describing planetary motions with remarkable effectiveness. For generations, the heavens remained ordered around Earth. Then scholars working across the medieval Islamic world preserved earlier astronomical traditions while testing, correcting, and extending them. Observatories and increasingly refined instruments made celestial measurement more precise. The sky slowly became numerical. Centuries later, Copernicus placed the Sun near the center of planetary motion. Tycho Brahe gathered exceptionally precise naked-eye observations, while Kepler discovered that planets followed elliptical rather than perfectly circular paths. Then glass changed everything. Galileo pointed telescopes toward the heavens and saw mountains on the moon, moons circling Jupiter, and phases of Venus that challenged older assumptions about cosmic organization. The heavens were no longer obviously perfect. Newton later showed that the force drawing an apple downward could belong to the same physical framework governing the moon and planets. Earth and heaven were becoming one system. Still, another question remained almost untouched. How old was Earth? For most of history, nobody possessed a reliable method for measuring geological time. Human records reached backward thousands of years, while Earth's rocks concealed durations measured in millions and eventually billions. You might hold an ordinary stone and see nothing unusual. A geologist eventually learned to see time. During the 18th and 19th centuries, researchers increasingly recognized that erosion, sedimentation, uplift, and other geological processes could require immense periods. Layered rocks seemed to preserve vanished environments stacked one above another. Earth acquired a history. There is a charmingly peculiar detail here. Before modern dating methods, serious researchers proposed wildly different estimates for Earth's age, using cooling rates, sediment accumulation, ocean chemistry, and even the sun's presumed energy supply. Some calculations sounded impressively precise. They were also impressively wrong. The missing ingredient was radioactivity, a phenomenon unknown to earlier investigators. Once scientists understood radioactive decay, certain minerals became natural clocks. Atoms could remember. During the 20th century, measurements of meteorites and ancient terrestrial materials gradually converged on an age near 4.54 billion years for Earth. Suddenly, human history became almost invisible by comparison. Imagine compressing Earth's entire existence into a single 24-hour day. Modern humans would arrive extremely late, and written civilization would occupy only the final moments. Yet there is an even deeper twist. Earth's oldest surviving materials are not necessarily the oldest ingredients from which Earth formed. Some atoms inside your body existed before the solar system. The iron carrying oxygen through blood belongs to a cosmic history older than oceans. Elements heavier than hydrogen and helium were produced through generations of stars and violent astrophysical events before our sun existed. So the history of Earth cannot truly begin with Earth. You must travel farther backward. Modern telescopes allow astronomers to observe distant regions where stars are forming today. Radio observatories detect cold molecular clouds invisible to human eyes, while infrared instruments peer through dust that blocks ordinary visible light. These observations provide analogues for our own distant beginning. Our solar system was born from material with a history. Some of that material came from earlier generations of stars. Some consisted of ancient hydrogen produced when the universe was young, long before oceans appeared. The atoms needed to make oceans were already traveling through space. Long before Earth's first rock hardened, silicon and oxygen existed inside a galaxy that had been evolving for billions of years, and long before anyone stood beneath a dark sky, wondering what the stars might be. Those stars had already participated in creating the observer. There is something quietly circular about that. You begin with humans looking upward, believing Earth might occupy the center of everything. You eventually discover that Earth is one planet around one star, among hundreds of billions in the Milky Way. Then the story becomes stranger again. The observer and the observed are made from the same cosmic material. The cool ground beneath you, the calcium in your bones, the iron in your blood, and the distant stars belong to one connected physical history. The night seems quieter now above you. Familiar constellations remain, where generations imagined hunters, animals, heroes, and gods. Those pictures were human inventions. But the curiosity behind them opened something real. To discover Earth's beginning, you must leave Earth behind. You must travel to a time before its oceans, before its rocks, and before the moon illuminated any night. There, inside a cold and slowly collapsing cloud. The next part of the story is waiting. The cloud waiting in darkness is enormous, cold, and almost impossibly thin. You drift through it without finding anything resembling a solid surface. There is no young Earth beneath you yet, and there is certainly no sun warming your imagined face. Only gas, microscopic dust grains, and darkness stretch across an immense region of space. Most of the material is hydrogen and helium. These simple elements carry you much farther into cosmic history than Earth's rocks ever could. Hydrogen was produced during the universe's earliest stages, billions of years before the solar system existed. Heavier elements arrived later, long before the sun appeared. Earlier generations of stars had lived and died throughout the Milky Way. Inside those stars, nuclear reactions built heavier elements from lighter ones. Some stars eventually returned enriched material to space. Carbon, oxygen, silicon, iron, and many other ingredients mixed gradually through the galaxy. Violent stellar deaths helped scatter additional heavy elements across enormous distances. Your future planet requires this inheritance. Without those earlier stars, there can be no rocky Earth, no iron core, and no minerals beneath future oceans. The solar system begins with recycled cosmic material. It is an oddly comforting thought. Nature wastes very little. About 4.6 billion years ago, somewhere within the Milky Way, part of a molecular cloud began collapsing. Astronomers cannot reconstruct the exact appearance of that vanished cloud. They can study similar nurseries today. Through radio and infrared telescopes, you can see cold clouds where new stars are forming behind curtains of dust. Dense knots contract, young stars ignite, and disks gather around them. Our own beginning probably shared important features with these environments. What triggered the collapse remains uncertain. A shock wave from a nearby stellar explosion might have compressed the cloud. Winds from massive stars could also have influenced the region. or ordinary gravitational instability may have been sufficient. Researchers still debate the Sun's precise stellar birthplace. Chemical fingerprints preserved in primitive meteorites offer tantalizing clues, but they do not provide a complete family photograph. So you watch the cloud contract without pretending to know every detail. Gravity does most of the work. A slightly denser region attracts more surrounding material. As mass accumulates, its gravitational pull becomes stronger, drawing additional gas inward. The process accelerates. Imagine the movement occurring across distances far beyond anything experienced on Earth. There is no roaring cosmic waterfall, despite what dramatic films might suggest. Space remains nearly silent. If sound could somehow reach you, the environment would not thunder like a storm. The drama lies in scale rather than noise. Gas falls inward over immense periods. As the cloud contracts, it begins rotating faster. Even a tiny initial rotation becomes important when enormous amounts of material collapse toward a smaller region. You know the principle from a spinning skater. Pulling mass inward increases the rotation rate. The collapsing material, therefore, cannot simply fall straight into the center. Rotation spreads much of it into a flattened disk around the growing central object. You now hover above the solar system before planets exist. At the center lies a protostar. Around it stretches a rotating disk of gas and dust, broad enough to contain the raw materials for worlds. Temperatures vary dramatically across this disk. Near the center, conditions are extremely hot. Farther away, colder regions allow volatile compounds and ices to survive. This temperature difference will eventually help explain why rocky planets dominate the inner solar system, while giant planets formed farther outward. But Earth is still only potential. You pass through the disk and encounter dust grains smaller than sand. They contain compounds built from elements inherited from ancient stars. Some grains collide gently, instead of immediately shattering. Certain particles stick through tiny electromagnetic forces. Clusters form, collide, and sometimes grow larger. This humble process will eventually produce planets. For now, the central protostar commands attention. Material continues falling toward it, increasing pressure and temperature deep inside. The young sun has not yet reached the stable condition familiar today. It is restless and energetic. Powerful magnetic activity and stellar outflows interact with the surrounding disk. Radiation pours outward as the central object continues contracting. Eventually, the interior becomes hot and dense enough for sustained hydrogen fusion. The sun enters its long main sequence life. Hydrogen nuclei combine through a chain of reactions, ultimately producing helium while releasing energy. That energy begins a journey outward through the solar interior. A photon does not simply race directly from the center into space. Its path can be astonishingly complicated. Energy produced deep inside interacts repeatedly with surrounding matter before eventually reaching the surface and escaping as radiation. Once free, sunlight crosses Earth's future orbital distance in a little over 8 minutes. There is no Earth to receive it yet. Only the disk remains. You can imagine its appearance from a safe distance. The young sun glows at the center, while dusty material forms a flattened structure around it. The smell of such a place is meaningless in the ordinary sense. There is no breathable atmosphere carrying scents toward a human nose. Yet the chemistry is rich. Primitive meteorites later preserve organic compounds, minerals, and tiny inclusions dating from the solar system's earliest history. Some of those inclusions are extraordinarily old. Calcium and aluminum-rich inclusions found in certain meteorites represent some of the earliest solids known to have condensed in the young solar system. Scientists date them to roughly 4,567 billion years ago. These tiny objects provide a practical starting clock for solar system formation. A fragment held in a laboratory can therefore connect directly with this vanished disk. That is one of geology's quieter marvels. You do not need a functioning time machine when matter carries measurable records of its own past. The disk itself changes continuously. Dust concentrates in some regions. Gas moves through others. Temperatures evolve as the young sun and surrounding material develop. Small particles migrate. Some fall inward and disappear into the star. Others become trapped in growing structures or transported across surprising distances within the disk. Planet formation is not a tidy assembly line. It is messy. Computer models show worlds migrating, colliding, exchanging material, and gravitationally disturbing their neighbors. Our familiar solar system is the survivor of that complicated youth. Even Jupiter may have influenced Earth's future before Earth was complete. The giant planet's gravity could alter the trajectories of smaller bodies, reshape reservoirs of material, and influence what reached the inner solar system. Exactly how the giant planets migrated remains an active field of research. Different models reproduce different features. The surviving planets provide clues, but much evidence from the earliest era has vanished through collisions, melting, and later geological activity. Earth is especially frustrating. Our planet continually destroys parts of its own ancient record. The Moon, asteroids, meteorites, and other planets therefore become pages from a family history that Earth itself partly erased. Modern astronomy adds another perspective. Telescopes now reveal disks surrounding young stars elsewhere in the galaxy. Some contain gaps and rings that may be associated with forming planets. You are watching other planetary systems construct themselves. Their details differ from ours, but the broader lesson is profound. The birth of planets is not a unique event, preserved only in theoretical equations. It is happening now, somewhere within distant stellar nurseries. Dust is colliding around newborn stars, while gravity quietly gathers matter into larger structures. Perhaps some will become rocky worlds. Our own disk once performed the same patient work. Around the newborn sun, countless microscopic particles continue meeting. Clumps become larger aggregates, and aggregates begin the difficult journey toward planetesimals. Gravity will soon become more important than surface forces. Then growth becomes violent. The peaceful image of dust circling a young star will give way to collisions between increasingly substantial bodies. Some will merge, others will fragment. A few will grow large enough to dominate their neighborhoods, consuming or scattering smaller neighbors as the inner solar system becomes crowded with unfinished worlds. One of them will become Earth, but it will not be blue. It will not be gentle. And before it can carry oceans beneath a quiet sky, it must first survive its own violent construction. Around the newborn sun, the quiet dust has begun to organize itself into something much more dangerous. You move through a disk crowded with particles, fragments, and increasingly substantial bodies. Some remain smaller than grains of sand, while others have grown into objects measured in kilometers. There is still no Earth. Instead, countless possible Earths compete for material within the hot inner solar system. Most of them will disappear before anything resembling the modern planets emerges. Growth begins gently enough. Dust grains collide at relatively low speeds and sometimes remain attached. Larger aggregates form. Although exactly how these small clumps crossed certain difficult stages of planetary growth remains an active research question. Tiny particles stick rather easily. Larger objects can become troublesome. When collisions grow energetic, bodies may bounce apart or fragment instead of merging. Researchers sometimes call part of this difficulty the bouncing barrier. Nature somehow crossed it. Local concentrations of solid material may have helped particles gather rapidly enough for gravity to become important. Once sufficiently large planetesimals appeared, the rules changed dramatically. Gravity now pulled objects together. Imagine looking across the inner solar system during this period. The young sun burns intensely nearby, surrounded by dusty light and countless moving fragments. There is no peaceful blue horizon. The environment carries no smell because there is no air for you to breathe. Yet if you could touch one of these rocky bodies safely, Its surface might range from cold rubble to material heated by impacts and radioactive decay. Collisions become frequent. A planetesimal passing near another has its trajectory bent by gravity. Sometimes the two miss each other, while other encounters end in impacts that add material to the larger body. The largest objects gain an advantage. Their stronger gravity allows them to capture more material, accelerating their growth. Some eventually become planetary embryos, unfinished worlds moving through crowded orbital neighborhoods. Earth begins somewhere within this chaos. You cannot point toward a single pebble and confidently announce that it is the beginning of our planet. Earth's material accumulated from many bodies over a long sequence of collisions. Its identity emerges gradually. Think of a city built from stones, gathered across an entire landscape, except the stones themselves are moving around the sun at extraordinary speeds. And occasionally, the city is hit by another city. The young Earth grows through repeated impacts. Some collisions are relatively modest. Others release enough energy to melt substantial portions of the developing planet. Each impact converts motion into heat. Additional heating comes from gravitational compression and radioactive isotopes present in early solar system material. The result is an increasingly hot, young world. Earth becomes large surprisingly quickly on geological timescales. Models suggest much of its mass accumulated within tens of millions of years after the solar system began forming. Exact details depend on how planetary accretion unfolded. The chronology is reconstructed indirectly. Meteorites provide some of the strongest evidence. Many meteorites are fragments of ancient bodies that never became full-sized planets. Their chemistry preserves information from the solar system's earliest stages. You can hold one in your hand today. Its dark surface might appear disappointingly ordinary. It does not glow, whisper, or provide dramatic background music. Cosmic artifacts are inconsiderate that way. Yet laboratories can measure isotopes within meteorites and extract astonishingly precise information about events billions of years ago. Some meteorites even contain tiny pre-solar grains. These grains formed before our solar system existed, probably around older stars, then survived the violent process that created the sun and planets. They are older than Earth. A microscopic grain can therefore have a biography beginning around a star that vanished before the planet beneath your feet existed. Meanwhile, the growing proto-Earth continues sweeping through its orbit. Nearby planetary embryos interact gravitationally. Their paths become unstable, and collisions between substantial bodies become increasingly likely. The inner solar system resembles a long competition. Mercury, Venus, Earth, and Mars eventually survive as recognizable rocky planets, but they are not necessarily the only large objects that once occupied this region. Other embryos were absorbed, shattered, or ejected. One hypothetical lost body has become particularly famous. Scientists often call it Theia. Its importance lies slightly ahead of you, because a collision between the proto-Earth and a roughly planetary-sized object provides the leading explanation for the Moon's formation. Before reaching that impact, however, Earth is already changing internally. As the planet grows and heats, portions of its interior melt. Dense materials, especially iron-rich metal, begin sinking toward the center. Lighter rocky material remains above. Earth starts differentiating into layers. This process eventually produces the metallic core, rocky mantle, and outer crustal regions that define the planet's internal architecture. Imagine sinking through that young Earth. There is no neat boundary marked by a sign announcing the mantle. Instead, pressure rises relentlessly while materials behave differently as temperature, density, and composition change. Metal migrates downward. That sinking releases additional gravitational energy as heat, making the early planet even more thermally active. Earth is effectively reorganizing itself by density. Gold offers a curious illustration. Many elements attracted to metallic iron would have followed sinking metal toward Earth's core during differentiation. Much of Earth's original inventory of certain valuable metals may therefore lie far beyond any possible mine. Later impacts probably delivered additional material to the mantle and crust, so the gold in a ring may represent only a tiny, accessible fraction of Earth's deeper elemental wealth. The young planet does not care about future jewelry markets. It has more immediate problems. Its surface is repeatedly disrupted by impacts, while volcanic gases escape from the hot interior. Any early atmosphere is unlike the oxygen-rich air you know. Free oxygen is essentially absent. Carbon dioxide, water vapor, nitrogen-bearing compounds, and other gases contribute to changing atmospheric conditions. Although reconstructing the exact composition is difficult, much of the evidence has been recycled. Geologists disagree about important details of Earth's earliest atmosphere, including how quickly particular gases accumulated and how strongly impacts altered them. The young sun complicates matters further. It was fainter overall than it is today, yet it was also magnetically active. Powerful ultraviolet radiation and solar particles interacted with planetary atmospheres. Earth needed to retain enough volatile material to become the world you recognize. Where that material came from remains a fascinating question. Water may have been incorporated into Earth's building materials from relatively early stages. Additional water-bearing bodies could have contributed during later accretion. Comets once received much of the popular attention. However, isotopic evidence indicates that many carbon-rich asteroidal materials provide a closer match for much of Earth's water than several well-studied comet populations. The answer may involve multiple sources. Planet formation rarely respects simple stories. You continue watching the proto-Earth orbit the young sun. It is larger now, hot enough for widespread melting, and internally divided into increasingly distinct layers. But the solar system remains unstable. Large embryos still cross dangerous neighborhoods. Gravitational encounters alter their paths, and the growing Earth has not finished collecting its final mass. Then another world approaches. You would not see it rushing directly toward Earth like a projectile fired from distant space. Both bodies are orbiting the sun, following trajectories shaped by a complicated gravitational system. Their paths intersect. The approaching object may be comparable in size to Mars, although modern simulations allow a range of possible masses and impact conditions. Details remain debated. What follows will be one of the defining events in Earth's history. The collision will reshape the planet, melt enormous quantities of rock, and throw material outward around Earth. From that debris, something new will gather. For the first time, the young Earth will gain the companion that still moves through your night sky today. The approaching world does not arrive beneath a peaceful sky. There is hardly a sky at all in the familiar sense. The young Earth is already hot, battered, and surrounded by gases released through impacts and volcanic activity. Then another planetary body crosses its path, roughly 4.5 billion years ago. According to the leading explanation, an enormous collision transformed Earth and created the material from which the Moon formed. The hypothetical impactor is usually called Theia. You should not imagine a small asteroid approaching a completed version of modern Earth. Theia was probably a planetary embryo, perhaps broadly comparable with Mars in scale. Earth itself was unfinished. Both worlds belonged to the violent final stages of terrestrial planet formation, when large bodies still moved through an unstable inner solar system. Their encounter happens quickly. As Theia closes the final distance, gravity accelerates the bodies toward one another. Rock does not behave like the solid stone beneath your feet under such extreme conditions. The impact releases staggering energy. Large regions melt almost immediately. Other material vaporizes, while enormous quantities of hot debris are thrown away from the collision. There is no sound traveling through surrounding space. Yet within the material itself, shock waves move through rock with destructive force. If your impossible observation point allowed sound, to reach you. The event would overwhelm any earthly comparison. The surface becomes incandescent. You would smell nothing because breathing here is impossible. But the chemistry around you consists of vaporized rock, metal, and gases heated beyond ordinary experience. There is no comfortable place to stand. Earth survives. That simple fact hides a complicated process. The collision does not merely knock a convenient moon-shaped piece from the planet. Instead, simulations suggest material from the impact forms a hot disk around Earth. Some debris escapes completely. Some falls back. The rest remains in orbit, colliding and gathering under gravity until larger structures emerge. The moon begins assembling from wreckage. Exactly how this happened remains debated. The classic giant impact model explains many important features, but increasingly precise measurements have forced researchers to refine the details. Earth and Moon have remarkably similar isotopic compositions for several elements. That similarity creates a puzzle. If much of the Moon came from a completely separate body, you might expect clearer chemical differences between lunar and terrestrial rocks. Researchers have proposed several solutions. Perhaps they are formed from material already chemically similar to Earth's neighborhood. Perhaps the impact mixed both bodies extremely thoroughly. Other models suggest higher energy collisions or different impact geometries. One particularly dramatic proposal describes a temporary structure called a synestia, a vast rotating mass of vaporized and molten rock produced after an energetic collision. The Moon might have condensed within such an environment. It is an extraordinary image. For a brief geological moment, Earth may have been so violently transformed that the familiar distinction between planet and surrounding disk became difficult to apply. The details are still being tested. What is much more certain is that lunar samples preserve evidence connecting the Moon closely with Earth's early history. Those samples arrived through one of humanity's greatest observational leaps. For thousands of years, people watched the Moon with naked eyes. Its changing phases offered a natural rhythm for measuring time. Its surface showed permanent dark and bright patterns, although their true nature remained mysterious. Ancient observers tracked its motion carefully. Babylonian astronomers became remarkably skilled at recognizing eclipse cycles. Greek thinkers debated whether moonlight came from the Moon itself or reflected sunlight. By the classical period, some scholars understood the basic geometry of lunar phases and eclipses, yet the Moon remained physically unreachable. Then telescopes arrived. In 1609 and 1610, Galileo examined the Moon through an improved telescope and saw irregular shadows along the boundary between lunar day and night. Those shadows implied mountains and depressions. The Moon was not a perfectly smooth celestial sphere. It had terrain. Centuries later, increasingly powerful telescopes mapped its surface in greater detail. Photography turned fleeting observations into permanent records. Then rockets crossed the distance. In July 1969, Apollo 11 astronauts Neil Armstrong and Buzz Aldrin stepped onto the lunar surface, while Michael Collins remained in orbit. For Earth science, the important treasure was rock. Apollo missions returned hundreds of kilograms of lunar material, allowing laboratories to investigate the Moon's chemistry and geological history directly. Those rocks helped strengthen the giant impact hypothesis. The Moon had become an archive because its surface lacks Earth's active weather, oceans, and widespread plate tectonic recycling. Ancient lunar terrain preserves impact history that Earth has largely erased. You can look upward and see part of Earth's missing geological record. The newly formed Moon, however, looks nothing like the quiet object seen tonight. It begins extremely hot. A global or nearly global lunar magma ocean probably existed, allowing minerals to separate as the Moon cooled. Dense minerals sank, lighter minerals floated upward and contributed to an early crust. One important mineral was plagioclase feldspar, which helped form the bright, ancient lunar highlands. The familiar dark plains came much later. Those darker regions, called Maria, are enormous basaltic plains created when lava flooded large impact basins. Ancient observers once imagined some were seas. The name survived even after their dry nature became clear. Back beside the young Earth, the newborn moon orbits much closer than it does today. It appears enormous in the sky. Tidal interactions between Earth and Moon begin changing both worlds. Earth rotates much faster than it does now, producing dramatically shorter days. The Moon raises tides in Earth's deformable materials. Those interactions transfer rotational energy and angular momentum through the Earth-Moon system. Gradually, Earth's rotation slows. The Moon moves outward. This retreat continues today. Laser measurements using reflectors placed on the Moon show that its average distance is currently increasing by roughly 3.8 centimeters each year. A human fingernail can grow by a comparable order of distance annually. The Moon is leaving at something resembling fingernail speed. There is your peculiar cosmic detail. Of course, the rate has not remained constant throughout geological history. Continents, ocean depths, tidal patterns, and Earth's rotation all influence tidal dissipation. Researchers reconstruct ancient day lengths using geological records. Some sedimentary layers preserve rhythmic patterns related to tides and orbital cycles, offering indirect glimpses of the Earth-Moon relationship deep in time. The Moon may also have influenced Earth's long-term stability. Its gravitational presence helps shape variations in Earth's axial tilt, although describing it as simply preventing chaotic climate changes would be too neat. Planetary dynamics are more complicated. Still, without the Moon, Earth's rotational history would certainly have been different. There is another consequence of the impact beneath you. Earth has been reheated profoundly. Any crust existing before the collision may have been heavily disrupted or destroyed. Vast regions of the planet return to molten conditions. A deep magma ocean spreads across much of the surface. Above it hangs an atmosphere containing vaporized and outgassed material. The Moon glows nearby. You are looking at two worlds recovering from the same catastrophe. Yet catastrophe is a human word. From the perspective of planetary formation, collisions like this are part of construction. Worlds grow because smaller worlds cease to exist separately. Creation and destruction become the same process. The Moon is perhaps the most beautiful surviving reminder. Billions of years later, humans will use its phases for calendars, its gravity for understanding tides, and its motion for testing gravitational theories. Poets will fill it with longing. Scientists will fill laboratories with its rocks. Children will look upward and assume it has always been there. Almost, but now you know the quieter truth. The Moon is not merely Earth's companion. It is evidence of an ancient collision from a time when our planet was still becoming itself. Below you, Earth remains molten. Heavy material continues settling inward, while lighter silicates dominate above. Heat radiates towards space, but cooling will take time. The brilliant surface slowly darkens. Eventually, solid material will begin surviving at the exterior. A crust will appear, disappear, melt, and form again. The age of planetary collision is giving way to another transformation. For the first time, Earth is preparing to grow something resembling a surface beneath the newborn Moon. Earth glows like something taken from a furnace. You would recognize its spherical shape, but almost nothing else feels familiar. There are no continents to orient you, no blue oceans, and no white clouds drifting over green landscapes. Much of the surface is molten rock. The giant collision has delivered enormous energy into an already hot young planet. Impacts, gravitational compression, radioactive decay, and internal differentiation have all contributed additional heat. Earth has become a world of magma. Imagine hovering safely above that surface. The glow beneath you ranges from brilliant yellow regions to darker red expanses where the outermost material has begun cooling. Huge currents overturn within the molten silicate below. The atmosphere is thick and hostile. Water vapor, carbon dioxide, nitrogen-bearing gases, sulfur compounds, and other substances escape from the hot interior. There is no oxygen-rich air. You cannot breathe here, and you cannot smell the volcanic gases directly. Yet if some impossible mask translated the chemistry into familiar sensations, sulfurous odors and scorched mineral notes would dominate. Heat would overwhelm everything. The surface beneath an imaginary boot would not merely feel hot. In many places, there would be no stable surface capable of supporting you. Earth is still sorting itself internally. During its earliest growth, much of the planet became hot enough for large-scale melting. Dense metallic material migrated downward, while less dense silicate rock remained above. Iron moved toward the center. With it traveled nickel and other elements that prefer metallic environments. This downward migration helped create Earth's core. The process is called differentiation, although the tidy word conceals a planetary-scale transformation. Imagine droplets and larger masses of molten metal sinking through silicate material. Their descent releases gravitational energy, producing still more heat. Eventually, Earth develops its broad internal architecture. At the center lies a dense metallic core. Above it stretches the enormous rocky mantle. Near the exterior, cooling material will eventually form crust. Those layers remain fundamental today. You live on an exceptionally thin outer skin, covering a planet whose interior is still hot enough to drive geological activity after more than 4 billion years. If Earth were reduced to the size of an apple, the crust would seem remarkably delicate. The comparison is imperfect, but emotionally useful. You spend your entire life on the skin. The core begins thousands of kilometers beneath you, completely inaccessible to drilling. Humanity has never sampled it directly. So how do you know it exists? The answer eventually comes from earthquakes. Much later, humans learn that seismic waves change speed and direction while passing through different materials. Some waves cannot travel through liquids at all. Earth becomes transparent through vibration. In 1906, British geologist Richard Dixon Oldham used earthquake data to provide important evidence for a central core. Then, in 1936, Danish seismologist Inge Lehmann studied seismic observations and proposed something more subtle. Inside the liquid outer core was another region, a solid inner core. You can appreciate the strange elegance of that discovery. Nobody had seen it, touched it, or drilled anywhere remotely close to it. The evidence arrived as faint vibrations traveling through the planet. Modern seismology continues refining that picture. The inner core is mostly iron and nickel and remains solid because enormous pressure raises the melting temperature of its material. Around it lies the liquid outer core. Motion within this electrically conducting liquid helps generate Earth's magnetic field through a process called the geodynamo. Whether a magnetic field existed immediately after Earth's formation is harder to establish. Ancient minerals can sometimes preserve magnetic information, but interpreting extremely old samples is difficult. Scientists continue debating exactly when Earth's long-lived geodynamo became established. The question matters because magnetic fields influence how planets interact with charged particles from their stars. Yet Earth's atmosphere is not protected by a simple invisible shield that makes atmospheric loss impossible. Reality is more complicated. Venus has no Earth-like global magnetic field and still possesses an extremely thick atmosphere. Mars lost much of its atmosphere through processes involving its smaller mass, geological evolution, solar interactions, and other factors. Planetary habitability rarely obeys one convenient rule. For now, however, the young Earth's magnetic story remains mostly hidden beneath the magma. Above, cooling begins. Space is cold, and Earth radiates heat outward. But a magma ocean does not necessarily freeze quickly. The thick atmosphere can trap outgoing radiation, slowing the loss of heat. Water vapor is especially effective at absorbing infrared radiation. The young planet is wrapped in its own insulation. Eventually, conditions change enough for minerals to crystallize. Different minerals solidify at different temperatures and pressures. Some crystals sink, others remain suspended or become incorporated into developing solid layers. The mantle gradually evolves chemically as material separates. This is not simply a pot of lava becoming a single uniform rock. It is a dynamic chemical system. One curious consequence involves elements that do not fit easily inside common mineral structures. As crystals form, certain incompatible elements tend to remain concentrated within residual melts. Over geological time, such chemical sorting contributes to the remarkable diversity of rocks found near Earth's surface. The planet is creating complexity through cooling. You can almost hear the future mineral collections becoming unnecessarily expensive. Above the magma, the moon still dominates the sky. It orbits much closer than today, while Earth spins much faster. A day may last only several hours during parts of this early period, although precise values depend on the uncertain details of the giant impact and tidal evolution. Sunrise follows sunset rapidly. There are no observers to complain. Tides raised by the moon affect the young planet. Although talking about familiar ocean tides would be premature, Earth's surface and interior themselves deform under gravitational forces. The planet is not rigid. Even modern solid Earth rises and falls slightly because of lunar and solar tides. Rock, given enough scale and time, behaves less stubbornly than it seems beneath your hand. The early mantle demonstrates this beautifully. Although mostly solid after later cooling, mantle rock can flow slowly over geological timescales. That slow movement eventually becomes central to plate tectonics. But the molten world beneath you has not yet reached that familiar regime. Its immediate task is losing heat. As thousands and then millions of years pass, the exterior becomes increasingly capable of maintaining solid material. Temporary crust forms. Impacts can destroy it. Hot mantle material can remelt it. New crust replaces what disappears. Finding surviving evidence from this period is extraordinarily difficult because Earth is unusually good at erasing its childhood. Plate tectonics, erosion, metamorphism, melting, and impacts have destroyed or transformed most of the planet's earliest rocks. The moon preserves ancient surfaces more generously. Earth keeps renovating, yet a few astonishing survivors remain. Tiny zircon crystals found in ancient rocks contain chemical information from Earth's first several 100 million years. Some zircons are more than 4 billion years old. They are smaller than ordinary grains you might notice while walking along a beach, yet they preserve clues about conditions on an Earth almost completely lost. Certain zircon evidence suggests liquid water and relatively cool surface environments may have existed surprisingly early. Interpretations remain contested. Researchers debate exactly what particular oxygen isotope signatures reveal about interactions among water, crust, and magma. Still, these crystals complicate the old image of the Hadean Earth as one uninterrupted inferno. The name Hadean encourages drama. It comes from Hades, the ancient Greek underworld, and early scientists understandably imagined an extremely hostile young Earth. Parts of that picture remain valid. The early planet experienced tremendous heat and enormous impacts, but Earth may also have cooled locally or globally sooner than once assumed. Perhaps solid crust appeared while other regions remained volcanically active. Perhaps water interacted with rocks earlier than expected. The young Earth was probably not one unchanging scene. It evolved constantly. You watch the glow slowly retreat from portions of the surface. Dark crust spreads across areas that once shone brightly. Cracks open where hotter material rises from below. Volcanic gases continue escaping. Meteorites still strike. The atmosphere remains thick with substances that would be dangerous to modern life. Yet something important has happened. For the first time since the Great Collision, Earth is beginning to maintain a persistent outer skin. It is fragile. It is repeatedly broken. But it is a surface. You could almost imagine standing there now, if temperature and atmosphere were somehow made survivable. Beneath your feet, newly solidified rock would still radiate warmth. Above you, the closer moon would appear enormous against a dark and turbulent sky. Around you, volcanic gases would drift through an atmosphere without birds, insects, leaves, or any living sound. Earth would feel empty. But emptiness is misleading. Water vapor already surrounds the planet. Hydrogen and oxygen are locked within minerals and gases. The ingredients for future oceans are present, even though familiar seas have not yet spread across the surface. The furnace is cooling. Soon, the crust will become more persistent, and the atmosphere will begin another transformation. Earth has built its core. It has organized its mantle. Now, it must learn how to keep a crust beneath a sky that still bears almost no resemblance to your own. The brilliant ocean of magma is beginning to lose its uninterrupted hold on Earth's surface. Dark patches now interrupt the glow. They are not continents, and they would offer little comfort to anyone attempting to stand upon them. They are fragments of cooling rock, fragile skins forming over an interior that remains extraordinarily hot. This is Earth's earliest crust. You watch one patch darken beneath a turbulent atmosphere, only to see fractures spread across it later. Molten material rises through those openings and consumes portions of the surface again. Nothing stays quiet for long. Large impacts still arrive from space. Although their frequency changes as the solar system evolves, each substantial collision can excavate rock, melt surrounding terrain, and alter the atmosphere. Volcanism adds its own restless rhythm. There are no breaking waves, rustling leaves, or animal calls. The loudest imaginable sounds come from geological activity itself, transmitted through rock and the increasingly substantial atmosphere. The smell would be thoroughly unpleasant. Sulfur-bearing gases mix with steam and other volcanic emissions. Fine particles and condensed droplets may sometimes fill the air above regions of active volcanism. You would feel heat radiating upward through the ground. Yet this world is cooling. That apparent contradiction defines much of early Earth. The interior can remain extremely hot, while the exterior loses enough energy to become solid. A crust forms because Earth's surface radiates heat into space faster than deeper material can replace it everywhere. The earliest crust was probably unlike most modern continental crust. Today, oceanic crust is largely basaltic, while continents contain abundant lighter, silica-rich rocks. Early Earth probably began with extensive mafic crust formed from mantle-derived melts, but those first surfaces rarely survived. Hotter mantle conditions encouraged vigorous melting and recycling. Impacts repeatedly disturbed the exterior, while dense crust could sink back into the mantle. Earth was constantly editing its first draft. You search for surviving pages and find almost none. The oldest widely accepted intact rocks are roughly 4 billion years old, with famous examples preserved in regions such as northwestern Canada. Some claims for even older rocks remain controversial because extreme metamorphism can complicate their interpretation. Tiny minerals preserve older evidence. Those ancient zircons become your most durable witnesses. Zircon is unusually useful because its crystal structure can incorporate uranium while largely excluding lead when it forms. Over time, radioactive uranium decays into lead at predictable rates. By measuring those isotopes, scientists can estimate when the crystal formed. A grain almost invisible against your fingertip can therefore contain a clock spanning more than 4 billion years. This ability would have astonished early sky watchers. For ancient observers, Earth's surface seemed permanent, while the heavens supplied obvious cycles. The moon changed shape, planets wandered, and stars returned seasonally. Rock appeared comparatively timeless. Modern science reversed that intuition. The stars are changing, certainly, But so is the ground. Earth has always been moving chemically, thermally, and mechanically. The zircon evidence offers an especially intriguing possibility. Some crystals, older than 4 billion years, contain chemical signatures interpreted as evidence that their parent magmas interacted with material altered near Earth's surface. Liquid water may have been involved. If those interpretations are correct, parts of Earth became cool enough for water-rock interaction surprisingly early. Not everyone agrees on the details. Geochemists still debate what particular zircon compositions reveal about ancient crust, temperatures, and the presence of stable surface water. The disagreement is valuable. These crystals have survived extraordinary geological abuse, but they are not straightforward photographs of Hadean landscapes. They require interpretation. You continue across the early crust. Above you hangs an atmosphere, produced partly through gases escaping Earth's interior and partly through material retained or delivered during planetary accretion. It contains essentially no free oxygen comparable with modern air. That comes much later. Nitrogen may already be important, while carbon dioxide and water vapor contribute strongly to atmospheric conditions. Other gases appear in smaller quantities. Volcanic eruptions release steam, carbon compounds, sulfur compounds, and nitrogen-bearing material from Earth's interior. The precise mixture changes through time. Earth's first atmosphere may have included hydrogen and helium captured from the surrounding solar nebula. Although such a light primordial envelope would have been vulnerable to loss, the atmosphere you are watching is therefore not necessarily Earth's first. It is one of several stages. The young sun strongly influences this evolution. Although its overall luminosity was lower than today's, it produced energetic ultraviolet radiation and intense activity. Light gases could escape from the upper atmosphere. Impacts could remove gases while also delivering new volatile materials. Volcanoes replenished others. The atmosphere became a constantly negotiated boundary between Earth and space. There is a quirky consequence of this unfamiliar chemistry. If you somehow carried a modern oxygen meter onto the early surface, it would report conditions utterly incompatible with human breathing. Yet oxygen atoms are everywhere. They are bound into rocks, water molecules, carbon dioxide, and countless minerals. What Earth lacks is abundant molecular oxygen, floating freely through the atmosphere. That distinction will become enormously important once life enters the story. For now, oxygen prefers chemical captivity. Carbon dioxide behaves differently. Volcanic activity supplies it to the atmosphere, where it contributes to greenhouse warming. This matters because the young sun is fainter than the modern sun. Standard models of stellar evolution indicate that the early sun produced significantly less total energy. You might therefore expect early Earth to freeze. Yet geological evidence eventually indicates that liquid water existed during very ancient periods. This tension became known as the faint young sun paradox. How Earth remained warm enough is still investigated. Higher concentrations of greenhouse gases probably played major roles, while atmospheric pressure, clouds, surface properties, and other factors may also have mattered. There is no single simple thermostat. Earth's climate system is already complicated before biology becomes important. Meanwhile, the surface continues reorganizing. You might be tempted to describe cracks and moving crust as plate tectonics, but caution is necessary. Modern plate tectonics involves rigid lithospheric plates moving over a weaker underlying mantle, with organized spreading centers, subduction zones, and related processes. Early Earth may not have operated that way. Its mantle was hotter. Its crust may have been thinner, weaker, and more easily recycled. Some researchers argue that forms of plate tectonics began extremely early. Others favor later transitions from different tectonic regimes. The evidence becomes increasingly uncertain as you move backward. Earth has erased too much. Perhaps portions of crust sank locally. Perhaps mantle plumes repeatedly broke through stagnant surface layers. Perhaps several styles operated at different places or times. The planet was experimenting, though not consciously, with ways of losing internal heat. Above this unstable crust, the atmosphere gradually cools. Water vapor remains one of its most important ingredients. As surface temperatures fall, conditions approach a threshold that will transform Earth's appearance. Steam cannot remain steam forever if pressure and temperature allow condensation. Clouds thicken, droplets form. You can imagine the first scattered rain falling onto hot rock and disappearing almost immediately as vapor. The hiss would be tremendous near sufficiently hot surfaces. Water returns upward, condenses again, and falls once more. This cycle may repeat countless times while cooling continues. Eventually, some liquid survives. Depressions collect water, impact basins, volcanic landscapes, and irregular crust provide places where it can remain longer. Exactly when extensive stable oceans appeared remains uncertain, partly because direct geological evidence from this age is so scarce. But the chemistry of ancient zircons suggests water may have become established remarkably early. Earth is approaching another identity. Until now, fire has dominated your view. Soon, water will begin competing with it. The change does not happen during one convenient global rainstorm, and the planet does not suddenly turn blue overnight. Cooling, condensation, impacts, volcanism, and atmospheric evolution overlap across immense spans of time. Still, imagine one particular moment. You stand impossibly on a dark piece of primitive crust. The ground feels warm beneath you, rough and newly formed. Volcanic haze obscures parts of the horizon, while the immense young moon shines through shifting clouds. Then something touches the rock beside you. A drop of liquid water. Another follows. Then another. The planet that began as colliding dust has acquired a core, mantle, crust, and atmosphere. Now the sky itself is preparing to fall. The first drops do not yet make an ocean. They strike dark volcanic rock, gather briefly inside shallow depressions, and sometimes vanish again into steam. Beneath the surface, heat continues rising from an interior still carrying enormous energy from Earth's formation. Above you, the atmosphere is heavy with water vapor. This is a strange Earth, suspended between fire and water. Stable oceans have not yet spread across the surface, but the ingredients needed to create them are already circulating through rock, atmosphere, and space. The question seems simple. Where did Earth's water come from? For generations, one popular image offered an elegant answer. Comets, rich in ice, supposedly bombarded the young Earth and filled its empty basins. It is wonderfully cinematic. Unfortunately, nature prefers complicated scripts. Modern evidence suggests Earth's water probably came from several reservoirs and processes. Some water was likely present within the materials that assembled the planet itself. Additional water arrived during later impacts. Water-bearing asteroids appear especially important. Many primitive carbon-rich meteorites contain hydrated minerals and chemical signatures broadly compatible with major portions of Earth's volatile inventory. Comets remain part of the investigation. Measurements of hydrogen isotopes reveal that some comets differ significantly from Earth's oceans, while others provide closer matches. The population is chemically diverse, so the old picture of dry Earth waiting for icy delivery trucks from the outer solar system is probably too simple. Earth may never have been completely dry. You can follow water backward into the disk that surrounded the newborn sun. Near the young star, high temperatures made ordinary water ice difficult to preserve. Farther outward, colder conditions allowed ice to become abundant. Yet water also existed chemically bound within minerals. Material moved through the disk. Planetary embryos scattered one another. The boundaries between supposedly dry and wet regions were never perfectly sealed. Earth accumulated from this mixture. The growing planet then heated dramatically. Water incorporated into minerals could be released through melting and volcanic activity. Steam entered the atmosphere as Earth's interior degassed. You stand near an ancient volcanic landscape. Cracks glow faintly in the distance. Dark rock stretches beneath clouds so thick that the sun appears only as a diffuse brightness. The air carries no breathable oxygen. If your imaginary equipment could reproduce the smell safely, volcanic sulfur compounds would sting your senses. Moisture would cling to every surface as hot vapor condensed against cooler rock. Thunder may roll through dense clouds. Rain begins again. The droplets are not necessarily part of one continuous storm, lasting millions of years. That familiar image is useful for storytelling, but far too literal. Condensation probably occurred through evolving cycles. Rain fell. Water collected. Some evaporated. More condensed as temperatures changed. Volcanic eruptions continued returning gases to the atmosphere, while impacts periodically disturbed the surface. Earth's hydrological cycle was being assembled. But before permanent oceans dominate the landscape, another reservoir deserves your attention. The mantle contains enormous quantities of water, not underground seas, sloshing inside giant caverns, despite occasional dramatic headlines. Instead, hydrogen can be incorporated within the crystal structures of minerals deep inside Earth. Certain high-pressure minerals can hold substantial amounts. A mineral called ringwoodite became famous when scientists found a tiny inclusion of it trapped inside a diamond brought upward from deep within the mantle. The discovery supported evidence that Earth's transition zone can store significant water chemically. So when you ask where Earth's water is, the answer extends far beneath the ocean floor. Some is inside the planet. This creates a long exchange between surface and interior. Volcanoes release water. Later, once organized tectonic recycling develops. Hydrated materials can carry water back downward into the mantle. Earth does not merely possess water, it circulates it. How early this deep cycle began remains uncertain because early tectonic behavior itself is disputed. Researchers continue debating when processes resembling modern subduction became established. That uncertainty accompanies you across the Hadean landscape. The surviving evidence is sparse. Tiny zircons provide clues, but nearly complete landscapes from this era have disappeared. You are reconstructing an entire planet from fragments. It is rather like trying to describe a vanished library using several surviving commas. Still, those commas are remarkably informative. Some ancient zircon chemistry indicates interactions between liquid water and crustal material more than 4 billion years ago. That suggests the surface may have cooled enough for persistent liquid water relatively soon after Earth's formation. How much water existed remains harder to determine. Perhaps substantial oceans formed early. Perhaps smaller seas and basins appeared first. Perhaps major impacts repeatedly vaporized portions of existing surface water before it condensed again. The answer may involve all three. Large impacts are particularly important. When a substantial asteroid strikes an ocean-bearing world, tremendous heat can vaporize water locally or even globally under extreme circumstances. During Earth's earliest history, such disturbances were more common than today. Yet vaporized water does not automatically disappear into space. Much can remain gravitationally bound. As the atmosphere cools, it condenses again. The ocean can return. This gives early Earth an unusual resilience. Its surface environment may repeatedly suffer catastrophic disruption without losing every ingredient needed for future habitability. The Moon quietly records part of this violent history. Its ancient highlands are crowded with craters. Earth was struck too. Our planet simply concealed most scars through erosion, volcanism, crustal recycling, and later, plate tectonics. Looking at the Moon is therefore like seeing an old family member who kept the photographs Earth threw away. Ancient humans noticed those lunar markings without understanding their origin. To the naked eye, the dark regions formed shapes that cultures interpreted in many different ways. Some saw faces or animals. Nobody could know those patterns preserved the history of planetary impacts. Only telescopes and spacecraft revealed their geological meaning. By the 20th century, Crater counting became one method for estimating relative ages of planetary surfaces. A heavily cratered landscape is generally older than a smoother surface that has been resurfaced more recently. Humanity had learned to read scars on other worlds. Those observations helped reconstruct the environment surrounding early Earth. Back on the surface, water is becoming increasingly difficult to remove. The planet continues radiating heat. As temperatures decline, a larger fraction of atmospheric water can remain liquid at the surface. Cloud systems spread above broad regions. Rainfall feeds temporary lakes and expanding basins. Water flows downhill. That simple behavior immediately begins changing the crust. Liquid water is an extraordinarily effective geological agent. It enters fractures. It reacts chemically with minerals. It transports dissolved material. Later, rivers will carry sediments across continents and oceans will reshape coastlines. For now, there may be little recognizable land. Primitive crust rises unevenly above growing bodies of water. Volcanic islands may emerge and disappear. Impact basins collect rainfall. The coastline, wherever one exists, is dark and barren. No plant anchors sediment. No moss softens the stone. No shell lies beside the water. You hear only rain, distant volcanism, wind, and waves beginning to move across young basins. Touch the water, and it would probably feel warm in many environments. Its chemistry may differ substantially from modern seawater. Dissolved minerals enter from rock-water interactions and volcanic sources. Salts gradually accumulate through long geochemical processes. Exactly how salty the earliest oceans became, and how quickly, remains uncertain. The atmosphere above them is also evolving. As water vapor condenses, its powerful greenhouse contribution decreases. Carbon dioxide becomes increasingly important in regulating surface temperature. Rainwater can dissolve carbon dioxide. Once liquid water interacts extensively with rock. Chemical weathering can begin transferring carbon into minerals and sediments. A planetary thermostat is slowly taking shape. It is not perfectly stable. Nothing about Earth's climate history will ever be perfectly stable. But interactions among atmosphere, water, rock, volcanism, and eventually life will help regulate climate over immense timescales. For the moment, life is still absent from your view. That distinction matters. Water is necessary for life as humanity knows it. But water alone does not guarantee biology. A planet can have oceans and remain lifeless. You stand beside one of Earth's expanding ancient basins. Rain taps against the black surface around you. Steam rises from warmer patches near volcanic terrain. The young moon hangs behind thick clouds. A wave reaches the primitive shoreline and slides across bare rock. Then another follows. There is nobody here to name this water. No sailor crosses it. No astronomer watches moonlight trembling across its surface. The planet has not yet become the living Earth. But the age before oceans is ending. The rain is no longer merely touching hot stone. It is beginning to stay. Rain is now falling onto a world cool enough to remember it. Water no longer disappears everywhere into steam after touching the surface. It gathers in depressions, runs across bare volcanic rock, and joins expanding bodies of liquid beneath heavy clouds. The transformation is gradual. There is no single morning when Earth awakens suddenly blue. Instead, cooling shifts the balance between vapor in the atmosphere and liquid water accumulating below. More rain can remain. Basins deepen beneath dark skies. Eventually, enormous areas of the young planet hold persistent water, and the first long-lived oceans begin defining Earth's surface. Exactly when this happened remains uncertain. Evidence from ancient zircon crystals suggests liquid water interacted with Earth's crust more than 4 billion years ago. Some interpretations place potentially habitable surface conditions surprisingly early in the Hadean. Direct evidence is scarce. Almost all crust from this period has been destroyed, transformed, or recycled during the billions of years that followed. You are exploring a world mostly erased. Still, Imagine standing beside one of these ancient seas. Rain whispers across the surface. Waves move toward a shoreline, made entirely of barren rock. There is no seaweed swaying beneath them, and no vegetation softening the landscape behind you. The smell would be mineral and volcanic. Sulfur compounds drift from active regions, while moisture hangs heavily in the atmosphere. Warm water touches the edge of dark basalt and retreats again. The moon looms much larger than today. Its stronger tidal influence contributes to energetic tides, although the precise behavior depends upon basin shapes, Earth's faster rotation, and the moon's changing distance. The coastline never truly rests. Water moves inland and withdraws, again and again. These repeated cycles begin doing something that molten rock alone could never accomplish. They weather the planet. Water penetrates fractures and reacts with minerals. Dissolved substances are carried away, while loose fragments can be transported toward lower ground. Rainfall slowly alters atmospheric chemistry as well. Carbon dioxide dissolves into water. Chemical reactions involving rock can eventually lock some carbon into solid materials, helping connect atmosphere, crust, and ocean. The foundations of Earth's carbon cycle are appearing. Volcanoes return carbon dioxide from the interior. Weathering removes some from the atmosphere. Later tectonic recycling will carry carbon through the planet and release portions again. Much later still, life will interfere magnificently with the entire arrangement. For now, geology performs the work alone. The young sun complicates the climate. It shines with only around 70% of the luminosity it possesses today during Earth's earliest history. A weaker sun should make surface water difficult to maintain, yet ancient geological evidence indicates liquid water existed. This is the faint young sun paradox you encountered earlier. Greenhouse gases offer much of the solution. Higher atmospheric concentrations of carbon dioxide, and possibly methane during later periods, could provide additional warming. Other atmospheric and surface effects may have contributed. Scientists continue investigating how these factors combined through Earth's earliest climate history. The exact atmospheric pressure is also uncertain. You should therefore resist imagining one permanent Hadean weather forecast. Early Earth probably changed repeatedly. Periods of relatively moderate conditions may have alternated with extreme disruptions caused by volcanism and large impacts. The oceans themselves could sometimes be disturbed dramatically. A sufficiently large impact transfers enormous heat into the atmosphere and surface. Seawater near the impact site can vaporize almost instantly. Truly enormous collisions might produce much broader episodes of ocean vaporization, depending on their size and conditions. Then Earth cools again. Rain returns. The sea reforms. This repeated destruction and recovery sounds almost absurdly dramatic, but early planetary history is not obliged to provide comfortable continuity. One scholarly dispute concerns the so-called late heavy bombardment. Lunar samples once encouraged the idea that impacts increased sharply around 3.9 billion years ago during a relatively concentrated bombardment episode. Later research complicated that picture. Some scientists favor a more extended decline in impact rates, while others retain versions of a distinct period of enhanced bombardment. The moon preserves evidence, but interpretation remains difficult. Whatever the precise pattern, young Earth experienced more large impacts than the modern planet. You would notice, even a distant impact could fill the horizon with brilliant ejecta and send disturbances through atmosphere, crust, and ocean. The sky might remain hazy afterward. Fine material settles gradually. Then rain begins cleaning the atmosphere again. Earth keeps recovering. There is a quirky feature hidden inside those raindrops. The water molecule touching your imaginary hand may contain hydrogen, whose history reaches almost to the beginning of the universe. Hydrogen is ancient. The oxygen joined the story later, produced through stellar evolution before the solar system formed. Every wave therefore combines material from different chapters of cosmic history. The ocean is a mixture of stellar ancestry. Humans will eventually discover this only after learning to break light into its component wavelengths. Spectroscopy, developed powerfully during the 19th century, reveals that atoms interact with light in characteristic ways. Astronomers find the same elemental fingerprints in distant stars that chemists measure on Earth. The heavens and Earth share chemistry. That realization quietly destroys another ancient boundary. The sky is not made from some fundamentally separate celestial substance. The calcium in stone and the calcium detected in stars obey the same physical rules. The hydrogen in ancient oceans belongs to the same universe as hydrogen glowing across distant nebulae. Human understanding needed thousands of years to reach that conclusion. The young ocean beneath you simply continues moving. It does not know it is cosmic. Beneath the water, hydrothermal systems may develop where seawater interacts with hot crust. Water enters fractures. It warms. Chemical reactions alter both fluid and rock. Hot, mineral-rich water then returns toward the ocean. Modern hydrothermal vents demonstrate how powerful these interactions can become. Some vent fluids exceed temperatures that would normally boil water at the surface, but enormous deep ocean pressures keep them liquid. Whether similar systems existed during the earliest oceans is highly plausible. Although their exact nature is difficult to reconstruct, these environments will later become important in debates about life's origins. But biology has not arrived yet. For now, hydrothermal circulation is chemistry without organisms. Minerals precipitate from fluids. Chemical gradients develop. Molecules move between environments. The stage grows more elaborate. Above the water, small areas of crust may rise above sea level. How much exposed land existed during the Hadean and early Archean remains debated. Some models suggest a largely ocean-covered Earth with scattered volcanic islands. Others allow more substantial emergent crust. The answer depends partly on how much continental-type crust had already formed. Modern continents are unusually buoyant. Their silica-rich rocks are generally less dense than oceanic crust, allowing them to stand higher. Creating those rocks requires geological processing. Early Earth is beginning that process. Melting, crystallization, hydration, and recycling can transform primitive crust into chemically distinct materials. Over immense spans of time, lighter crustal components accumulate. The first enduring continental nuclei will eventually emerge. They will be small compared with today's continents. There is no recognizable Africa, Asia, Europe, or America. Every modern map remains impossibly far away. You might stand on a volcanic island that will later vanish completely into the mantle. Nothing guarantees preservation. That impermanence is one reason the ancient Earth feels so mysterious. The planet continually destroys evidence while creating new landscapes from the remains. Water accelerates this process. It erodes exposed rock and transports sediment. It alters minerals chemically. It can weaken portions of the lithosphere and influence melting. Some researchers have proposed that abundant water helped Earth develop its unusual tectonic behavior. Exactly when recognizable plate tectonics began remains unresolved. Evidence has been interpreted as supporting dates ranging across much of early Earth history. Perhaps modern-style plate tectonics emerged gradually rather than beginning on one particular afternoon. Earth rarely respects neat boundaries. As you watch, rain begins easing. Clouds thin enough for sunlight to spread across the water. The young sun is fainter, but its reflection still forms a bright path across the restless surface. There is no green anywhere. No animal breaks the waves. No oxygen-rich breeze crosses the shore. Only water, rock, atmosphere, and heat exchange energy beneath the enormous moon. Yet the planet has crossed another threshold. Once, Earth was primarily a growing collection of colliding solids. Then it became molten. Then crust appeared. Now liquid water covers vast portions of its exterior. The ocean introduces a new arena where molecules can dissolve, concentrate, react, separate, and recombine. Rain continues feeding it. Rivers, where exposed land allows them, begin carrying dissolved minerals toward it. Hydrothermal fluids enter from below. Material from space still arrives from above. Earth has built an enormous chemical laboratory. For perhaps the first time, you could look across its surface and recognize something emotionally familiar. A shoreline, a cloudy sky, rain touching water. But the resemblance ends there. The world remains silent in the biological sense. There is still no life known to be watching the waves. Soon, the ancient crust beneath those waves will begin organizing into more persistent pieces, while tiny surviving minerals preserve clues to landscapes that disappear. The oceans have arrived. Now, Earth must begin building the foundations of continents. Beyond the young ocean, pieces of dark land rise intermittently through mist and volcanic haze. They are not continents in the modern sense. There is no broad Eurasian interior, no recognizable African coastline, and no mountain chain resembling anything on a modern map. Much of the exposed surface may consist of volcanic islands and primitive crust. Earth is still constructing durable land. You approach one of these ancient shores while waves break against bare stone. Spray settles cold against the rock, although nearby volcanic ground still radiates heat through cracks and dark lava fields. The atmosphere smells strongly mineral and volcanic. Wind crosses the water without carrying pollen, soil, leaves, or the scent of vegetation. There is not yet anything resembling a forested coastline. Only geology meets the sea. The crust beneath you has become more complicated than the earliest basaltic surface. Repeated melting can separate materials chemically. Some melts become richer in silica and lighter elements, producing rocks more buoyant than primitive oceanic crust. These materials resist sinking as easily into the mantle. Gradually, persistent fragments accumulate. They become early continental nuclei. Much later, geologists will call ancient stable interiors of continents cratons. These regions preserve some of the oldest surviving rocks on Earth. You can visit pieces of them today. Ancient terrains survive in Canada, Greenland, Australia, southern Africa, and several other regions, although their rocks have often been altered profoundly. The oldest chapters are scattered. One famous survivor is the Acasta gneiss of northwestern Canada, containing rocks roughly 4 billion years old. Other ancient rocks have produced competing age claims. The Nuvvuagittuq greenstone belt in Canada contains extremely old material, but determining exactly how old some components are has generated substantial scientific debate. Dating the earliest Earth is difficult. A rock can experience melting, metamorphism, deformation, and chemical alteration long after it originally formed. Its isotopic clocks may be disturbed. You are trying to determine a birth date after several billion years of geological renovations. Fortunately, zircon is stubborn. You return again to those tiny crystals because they preserve information that most rocks cannot. The most famous, very ancient zircons come from the Jack Hills region of Western Australia. Some are about 4.4 billion years old. They are older than any intact rock currently known with comparable confidence. Imagine holding one. You would need magnification to appreciate it properly. The crystal might be smaller than a grain of sand, hardly the sort of object expected to rewrite planetary history. Yet its uranium and lead isotopes preserve extraordinary ages. Its chemistry provides additional clues. Some Jack Hills zircons appear to have formed from evolved magmas rather than directly from primitive mantle-derived melts. That raises a fascinating possibility. Earth may have developed chemically differentiated crust surprisingly early. Perhaps processes capable of generating continental-like material were operating within the first few 100 million years. How similar those processes were to modern plate tectonics remains uncertain. This is where the evidence becomes especially slippery. Some geologists interpret ancient chemical signatures as evidence for early subduction or related recycling. Others argue that similar signatures could emerge through different processes on a hotter young Earth. The disagreement is not merely about dates. It concerns how an entire planet worked. Modern Earth is dominated by plate tectonics. Its outer shell is divided into moving plates. New oceanic crust forms along spreading ridges, while older lithosphere descends at many subduction zones. Continents collide, mountain ranges rise, ocean basins open and close. But you cannot simply project that machinery backward unchanged. Early Earth contained more internal heat. Radioactive isotopes produced more heat than they do now, and residual energy from planetary formation was greater. The mantle may have convected more vigorously. Crustal thickness and strength differed. A hotter planet might support smaller, faster-moving plates, or perhaps weak crust behaved in ways that prevented stable modern-style subduction. Researchers model several possibilities. One involves a stagnant lid, where much of the outer shell remains comparatively immobile while hot material rises beneath it. Another involves episodic overturns. Still others propose early mobile lid behavior with important differences from modern tectonics. The surviving rocks refuse to provide a simple verdict. Earth's childhood remains annoyingly private. You walk farther inland across imaginary ancient terrain. There is still no true soil in the biological sense familiar today. Modern soils contain organic material, microbial communities, roots, burrowing organisms, and complex horizons. Here, weathering produces loose mineral debris. Rainwater reacts with exposed rock. Temperature changes and chemical alteration weaken surfaces. Sediment collects in low areas. Streams may flow across the landscape where elevation and rainfall allow them. Their banks are completely bare, without plants stabilizing sediment. Erosion behaves differently. Water can move loose material readily across exposed surfaces. Eventually, sediments enter lakes or oceans and settle into layers. Those layers become another form of memory. Sedimentary rocks preserve ancient environments through grain sizes, chemical signatures, structures, and mineral compositions. Later, geologists will learn to read them almost like documents. Ripples can preserve flowing water. Cracks can record drying mud. Rounded grains can reveal transport. Chemical deposits can indicate vanished oceans. A landscape disappears, yet its behavior survives inside stone. One particularly strange archive comes from tiny zircon inclusions. Minerals trapped inside zircon during crystal growth can preserve clues about the magma from which the zircon formed. The crystal becomes a geological safe. The safe is microscopic. Naturally, Earth chose the least convenient filing system imaginable. These ancient records suggest that the Hadean may have included more diverse surface conditions than older textbook images implied. Rather than one endless molten nightmare, portions of the planet may have supported crust, liquid water, and active geochemical cycling relatively early. That does not make Earth peaceful. Large impacts still occur. Volcanoes remain widespread. The atmosphere would remain deadly to you. Temperatures and climate could shift dramatically, but a planet capable of maintaining oceans and crust has already traveled far from its magma ocean beginning. The growing land also changes ocean chemistry. Rain falls onto exposed rock and carries dissolved ions toward the sea. Hydrothermal systems contribute material from below. Volcanic gases interact with water from above. Salts accumulate. Modern seawater contains sodium, chloride, magnesium, sulfate, calcium, potassium, and many other dissolved substances. The earliest ocean's composition was different. Reconstructing its salinity is challenging because direct samples obviously do not survive. Fluid inclusions and ancient minerals provide later clues. Scientists continue debating how seawater chemistry changed through deep time. Even the color of the ancient ocean is uncertain. Pure deep water tends toward blue because of how water absorbs light. But dissolved materials, suspended particles, atmospheric haze, and later, biological activity can alter appearance. Your imagined Hadean Sea might not resemble a tropical postcard. Under volcanic skies, It may look dark, gray, greenish, or metallic, depending on local conditions. The moon continues pulling on it. Earth continues spinning rapidly. Days slowly lengthen as tidal interactions transfer rotational energy through the Earth-Moon system. The process is almost imperceptible on a human timescale. Across hundreds of millions of years, it becomes profound. Everything here operates through accumulated small changes, punctuated by occasional catastrophes. Continental growth follows the same pattern. Fragments form. Some survive, others are recycled. Surviving pieces collide and join. Over time, larger bodies of buoyant crust emerge. Eventually, the planet will assemble and dismantle entire supercontinents. Those grand cycles lie far ahead. For now, you stand on land that may have no future. Perhaps this island will sink. Perhaps its rocks will melt. Perhaps several zircon crystals will survive and become trapped within younger sediment billions of years later. Those crystals might eventually be discovered by humans. Humans themselves remain almost unimaginably distant, yet their future curiosity is already being prepared. Earth is leaving evidence. Not much, but enough. One day, geologists will measure isotopes inside these minerals and reconstruct an age when no ordinary rock record survives intact. They will discover that the oldest pieces of Earth are not dramatic mountain ranges. They are tiny crystals. The mist thickens over the ancient shoreline. Rain begins tapping against bare rock again, washing minerals toward the ocean below. Behind you, volcanic highlands rise from primitive crust. Ahead, waves move beneath a moon still much closer than the one humans will know. Earth now possesses oceans and fragments of persistent land, but above and beyond them, the solar system remains dangerous. Many leftover bodies still wander through space. Some are small, others are large enough to alter entire regions of the planet. And Earth's ancient surface is about to discover how difficult it is to preserve a landscape beneath a sky still filled with falling worlds. Above the young oceans, the night sky is not empty. Countless objects still occupy the evolving solar system, leftovers from planetary construction that never became permanent planets. Some are small fragments, while others are substantial bodies moving along orbits shaped by the giant planets. Earth remains a target. You stand beside an ancient shoreline beneath a hazy sky. Waves strike bare rock with a steady rhythm, while the closer moon hangs enormous above the horizon. Then a new point of light appears. At first, it could resemble an unusually bright star. Over successive moments it grows, crossing the sky toward a world that has already survived billions of smaller collisions. There is no warning system. There is only impact. A large asteroid enters the atmosphere at tremendous speed. The air ahead of it compresses and heats intensely as the object plunges toward the surface. The final collision happens almost instantaneously. Rock melts. Material is thrown high above the surface. Shock waves travel outward through crust and atmosphere, while enormous quantities of dust and vapor spread from the impact region. If the body strikes ocean, water becomes part of the violence. Huge volumes can vaporize near the impact site. Waves spread outward across ancient basins, while heated material rises through the atmosphere. Then debris begins falling. Some particles return quickly, others remain aloft longer, affecting how sunlight reaches the surface. Earth has been struck again. During the planet's earliest history, scenes like this occurred far more often than they do today. Planet formation had left behind abundant debris. Gravitational interactions among planets continued disturbing smaller bodies, sometimes sending them toward the inner solar system. The moon preserves the evidence beautifully. Its ancient highlands are covered with overlapping craters, each marking a collision that occurred before erosion could erase it. Earth received a comparable history of impacts, but our planet hides its scars. Rain erodes crater walls. Sediments fill basins. Volcanism resurfaces landscapes. Tectonic recycling can eventually carry ancient crust back into the mantle. The oldest impact record therefore survives more clearly on the Moon than on Earth. This absence once encouraged a dramatic hypothesis. When Apollo astronauts returned lunar rocks, researchers found that several samples appeared to record major impact events around 3.9 billion years ago. Perhaps, scientists proposed, the inner solar system experienced a sudden spike in collisions. The idea became known as the Late Heavy Bombardment. For decades, it provided a powerful image of early Earth. A relatively calmer period was followed by an intense rain of asteroids, possibly triggered by rearrangements among the giant planets. Jupiter and Saturn may have shifted their orbits. Uranus and Neptune may also have migrated substantially. Smaller bodies could have been scattered throughout the solar system. Some inevitably reached Earth and Moon. The basic concept of planetary migration remains important, but the bombardment story has become less tidy. Researchers still argue over whether there was a sharp impact spike near 3.9 billion years ago or a more prolonged decline from earlier intense bombardment. Some lunar ages may reflect particular large basins rather than one global cataclysmic episode. New samples and improved dating continue refining the picture, so you should imagine danger without insisting upon one exact schedule. Earth was struck frequently. The precise rhythm remains uncertain. One especially quirky problem involves the rocks brought home by Apollo astronauts. Many samples came from areas influenced by enormous ancient impacts. Material thrown across the Moon by one giant basin-forming event can contaminate distant locations. A rock collected far away may therefore carry the age of an impact that occurred elsewhere. The Moon has mixed its paperwork. Scientists must carefully untangle it. Modern lunar missions are helping. Samples collected from different geological regions can test whether the impact ages measured from Apollo material truly represent moon-wide events. Human understanding improves by visiting new places. The same principle transformed astronomy long before spacecraft. Ancient Babylonian observers recorded eclipses and planetary positions because repeated observations revealed patterns invisible during a single lifetime. Tycho Brahe later pushed naked-eye precision to extraordinary levels. Telescopes expanded the evidence again. Spacecraft then allowed scientists to place instruments directly on other worlds. Each improvement changes what questions can be answered. The early bombardment is a perfect example. Earth alone cannot tell the whole story. You need the Moon. You need meteorites. You need asteroid chemistry and orbital models. You need computer simulations capable of following gravitational interactions over immense spans of time. A planetary history becomes a solar system history. Back on young Earth, the consequences of repeated impacts depend greatly on size. Small objects burn, fragment, or create limited craters. Larger bodies can devastate enormous regions. The very largest early impacts may affect global climate and surface conditions. An impact powerful enough to vaporize significant ocean water does not necessarily remove that water permanently. Much remains gravitationally bound to Earth. After temperatures fall, vapor condenses, clouds gather, rain returns, the ocean reforms. You have seen this rhythm before. Destruction is followed by cooling. That resilience becomes important when you approach the question of early life. Could organisms survive an era of giant impacts? If life already existed during some bombardment periods, surface environments might occasionally become extremely hostile. Yet subsurface habitats could offer protection. Deep ocean environments and crustal pores might remain comparatively sheltered from some catastrophes. Scientists debate how sterilizing the largest early impacts could actually have been. Completely sterilizing an entire planet is difficult. Once biology appears, it may prove remarkably persistent, but you have not reached secure evidence of life yet. For now, impacts are still participating in prebiotic chemistry. Asteroids and comets do more than excavate craters. They deliver material. Primitive meteorites contain carbon compounds, including amino acids and other organic molecules relevant to life's chemistry. This does not mean meteorites delivered living organisms. It means some ingredients associated with biology can form naturally without life. Organic chemistry is cosmic. The famous Murchison meteorite, which fell in Australia in 1969, contains a remarkable variety of organic compounds. Laboratory analysis revealed numerous amino acids and other carbon-rich molecules. Such discoveries changed how scientists imagined early Earth's chemical inventory. The sky could supply complex ingredients. Earth could produce others locally. Hydrothermal systems, atmospheric reactions, mineral surfaces, and impact chemistry all provided additional pathways. The young planet was receiving and manufacturing molecular possibilities. Meanwhile, impacts themselves could create temporary chemical environments. Heat alters minerals. Shock pressures produce unusual reactions. Impact-generated hydrothermal systems can persist after large collisions, circulating hot water through fractured crust. A crater begins as destruction and can later become a chemical reactor. Nature remains irritatingly unwilling to separate catastrophe from opportunity. You look again toward the moon. Its battered face records the era Earth mostly erased. Ancient observers could see its dark and bright regions, but lacked the instruments needed to identify craters clearly. Galileo's telescope revealed rough terrain. Later mapping recognized enormous basins. Spacecraft photographed them from orbit. Astronauts finally walked among lunar rocks. By measuring radioactive isotopes, scientists turned those rocks into clocks. The human story of cosmic discovery has reached backward through matter itself. A Babylonian observer could predict certain eclipses by watching celestial cycles. A modern geochemist can estimate when a lunar basin formed by counting atoms inside a mineral. Both are reading time. Their instruments are different. Their instinct is the same. Observe carefully enough, and the universe begins surrendering its history. Another impact flashes somewhere beyond your imagined horizon. The ground trembles faintly beneath you. Minutes later, atmospheric disturbances arrive. Much later, fine debris settles onto ancient water. Earth continues turning. Its day is still shorter than yours. Its moon continues retreating slowly. Its crust continues forming, melting and recycling. But something important is changing within the solar system. The great construction site is being cleared. As leftover objects collide, become incorporated into planets, fall into the sun, or are ejected into distant space, the frequency of enormous impacts gradually declines. Earth gains longer intervals of comparative stability. Not peace. This planet will never receive a permanent guarantee of peace. Asteroids will return throughout geological history, including one that will become famous for ending the age of non-avian dinosaurs. But the extraordinary violence of planetary formation is fading. The ancient ocean survives another disturbance. Rain falls through dusty air. Water runs across fractured rock and enters a crater still warm from impact heating. Below the surface, heat drives circulation through newly broken crust. Chemicals dissolve and recombine. The crater slowly becomes part of Earth's geology. Above it, fewer giant objects cross the sky than before. The planet has endured the era when worlds were assembled through collision. Now another force will increasingly shape its surface from within. Earth's stored heat is still rising. Its mantle is still moving. And beneath the battered crust, the planet is preparing to recycle itself. The sky is becoming less dangerous, but the ground beneath you is anything but quiet. Earth no longer needs a constant rain of giant asteroids to transform its surface. Enough energy remains trapped inside the planet to rebuild landscapes from below. You stand on ancient crust beside a dark ocean. The rock feels solid beneath your feet, yet deep below. The mantle moves with extraordinary patience. Heat left from planetary formation joins heat released by radioactive decay. That energy must escape. Earth begins losing it through a restless combination of conduction, volcanism, mantle circulation, and the recycling of crustal material. The modern planet performs much of this work through plate tectonics, but you are still too early to assume the same machinery operates beneath you. The young mantle is hotter. Its circulation may be more vigorous, while the crust above behaves differently from the comparatively mature lithosphere familiar today. Researchers continue arguing about when modern-style plate tectonics truly began. Some evidence suggests forms of mobile crustal recycling very early in Earth history. Other interpretations favor a later transition. The difficulty comes from preservation. The process you are trying to reconstruct is remarkably good at destroying the evidence needed to reconstruct it. Subduction carries old crust downward. Metamorphism alters surviving rocks. Melting erases earlier structures. Billions of years later, geologists are left interrogating fragments. Still, the planet provides clues. You move across primitive crust until the landscape rises into volcanic highlands. Dark lava flows overlap one another, while gases escape from fractures. The air remains oxygen-poor. Moisture settles against exposed stone, and sulfurous volcanic smells would dominate any impossible breath you attempted here. A low geological rumble travels beneath your feet. Somewhere below, hot mantle material is rising. Earth's mantle should not be imagined as a global ocean of liquid magma. That misconception is surprisingly persistent. Most of the modern mantle is solid rock. Yet solid rock can deform and flow slowly when subjected to enormous temperatures, pressures, and geological timescales. Warm material becomes buoyant and rises. Cooler material can descend. This slow circulation helps transfer heat outward. Early Earth may have performed this process more energetically. Large upwellings could produce enormous quantities of magma. Volcanic activity builds new crust elsewhere. Older material sinks or becomes buried and transformed. The surface is being recycled. Whether you should call every part of this process plate tectonics depends on definitions and evidence. Modern tectonic plates are coherent sections of lithosphere separated by recognizable boundaries. At mid-ocean ridges, mantle material rises and produces new oceanic crust. At subduction zones, dense oceanic lithosphere descends back into the mantle. Transform boundaries allow plates to slide laterally past one another. Continents ride within this moving system. Nothing remains geographically permanent. The Atlantic Ocean did not always exist. India once traveled independently before colliding with Asia. Antarctica once supported forests. The quiet ground beneath a modern city may have crossed enormous distances through geological time. Human beings discovered this remarkably late. For most recorded history, continents appeared fixed. Their shapes were simply part of the world. Then maps became accurate enough for an obvious curiosity to become difficult to ignore. The coastlines around the Atlantic seem to correspond. South America and Africa provide the most famous example. Several thinkers noticed the resemblance before the 20th century, but resemblance alone could not demonstrate movement. In 1912, Alfred Wegener publicly developed the idea of continental drift. He assembled evidence from matching fossils, rock formations, ancient climates, and continental shapes. He argued that continents had once been joined. The idea was bold. It was also missing a convincing mechanism. Many geologists rejected it. Wegener could describe evidence suggesting movement, but he could not adequately explain how continents traveled through Earth's crust. The criticism was reasonable. A correct idea with an incorrect mechanism still has serious problems. Then the ocean floor changed the argument. During the 20th century, sonar mapping revealed enormous underwater mountain systems. Mid-ocean ridges crossed the seafloor. Measurements of Earth's magnetic field added another clue. As basalt cools, iron-bearing minerals can preserve the direction of the surrounding magnetic field. Earth's magnetic polarity has reversed many times. The north and south magnetic poles have exchanged orientations repeatedly through geological history. New crust, forming along mid-ocean ridges, records those reversals. Scientists discovered symmetrical magnetic stripes on opposite sides of ridges. The ocean floor was spreading. This was the missing architecture. New lithosphere formed at ridges. moved outward, and eventually disappeared into deep ocean trenches through subduction. By the 1960s, plate tectonics unified enormous areas of geology. Earthquakes, volcanoes, mountain belts, ocean trenches, and continental motion suddenly belonged to one coherent framework. Humanity discovered that solid ground travels. Now return to the early Earth. You know what mature plate tectonics eventually becomes, but its beginning remains hazy. Some ancient rocks contain chemical signatures resembling those produced in modern subduction environments. Others preserve evidence of crustal deformation and recycling. Yet similar signals might arise through processes unique to a hotter planet. Scholars disagree over whether plate tectonics began in the Hadean, Archean, or significantly later. Perhaps the question itself is too simple. There may have been no single starting moment. Earth could have passed through transitional tectonic regimes, with localized subduction appearing before a stable global network of moving plates. The machinery may have assembled gradually. That possibility feels appropriate. Planets rarely switch operating systems overnight. Whatever terminology you choose, crustal recycling has profound consequences. It helps build differentiated continental material. It transfers water and carbon between the surface and interior. It creates diverse geological environments. It exposes fresh rock to weathering. It produces volcanic arcs, basins, fractures, and hydrothermal systems. All of these influence Earth's chemistry. You approach one such hydrothermal region beneath the ancient ocean. Seawater enters fractures in hot crust. It descends, warms, and reacts chemically with surrounding rock. The fluid becomes enriched with dissolved minerals. Then it rises. Where hot fluid encounters colder ocean water, minerals precipitate. Structures can grow around the venting fluids. There is no need for biology to create this chemical complexity. Rock and water are sufficient. The gradients are important. Hot and cold meet. Acidic and alkaline environments can meet. Reduced chemicals encounter more oxidized substances. Energy becomes available through chemical disequilibrium. Such environments are central to several hypotheses about life's origin. Some researchers favor alkaline hydrothermal vents, where natural mineral compartments might have concentrated molecules and supported useful chemical gradients. Others argue that surface environments offered better conditions. The debate lies ahead. For now, notice what tectonic and volcanic activity provides. Earth is not a passive container holding an ocean. It continually creates new chemical opportunities. Even continents participate. As lighter crust accumulates and survives, more land may rise above sea level. Rain falls onto fresh rock. Weathering releases nutrients and dissolved ions. Rivers carry them toward the ocean. Sediments accumulate along margins. Shallow coastal environments become chemically different from the deep sea. Earth develops variety. That may be one of its most important characteristics. A perfectly uniform planet offers fewer environmental gradients. Earth instead creates boundaries everywhere. Ocean meets land. Water meets rock. Hot fluid meets cold seawater. Atmosphere meets surface. Sunlight meets darkness. Chemistry thrives at boundaries. One peculiar example appears in modern subduction zones. Water carried downward within minerals lowers the melting temperature of mantle material above a descending plate. This promotes magma formation. Water helps generate volcanoes. The same substance falling as gentle rain can therefore participate in processes that eventually produce explosive volcanic arcs. Earth appreciates irony. The ancient version of this cycle remains uncertain, but interactions among water and hot crust certainly occurred. You can feel the consequences beneath your imaginary feet. The ground trembles. A fracture opens somewhere across the volcanic terrain. Magma rises through crust that has already been rebuilt many times. Eventually, lava reaches the surface and cools. New rock replaces old rock. The cycle continues. Above, the sun crosses a sky still chemically alien to you. The moon moves through a shorter month at a smaller orbital distance. Below, Earth's interior slowly loses heat. This process will continue for billions of years. The planet is cooling, but it is nowhere near geologically dead. Even today, continents drift several centimeters each year. Mountains rise, ocean floors spread, earthquakes release accumulated strain. Volcanoes return deep material to the surface. You live on the moving result. But here, in deep time, the system is younger, hotter, and less clearly organized. The ancient crust keeps breaking, melting, sinking, and reforming. Oceans circulate through fractured rock. Minerals react. Carbon moves. Water moves. Energy flows through countless gradients. And somewhere within this increasingly varied planet, chemistry is approaching a remarkable threshold. Not life yet, but something closer. Earth has learned how to recycle itself. Now, its rocks, water, atmosphere, and energy can begin assembling combinations that geology alone has never produced before. Along the ancient shoreline, the world looks empty. Rain darkens bare rock beside a restless ocean. Warm water gathers inside shallow pools, while volcanic gases drift through an atmosphere without breathable oxygen. Nothing crawls across the stones. Nothing grows toward the light. Yet emptiness does not mean inactivity. Inside the water, molecules collide constantly. Minerals dissolve from rock. Carbon compounds circulate through the environment. And energy arrives from sunlight, geothermal heat, electrical storms, and chemical reactions. Earth has become a laboratory without a chemist. The ingredients are not all produced here. Meteorites continue delivering carbon-rich compounds from space. Primitive meteorites demonstrate that amino acids and other organic molecules can form naturally without biological activity. Organic does not mean alive. It simply refers broadly to carbon-containing chemistry of particular kinds. That distinction is essential. You can produce some building blocks associated with life without producing anything capable of reproduction, metabolism, or evolution. The gap remains enormous. Still, chemistry has begun crossing interesting thresholds. Imagine kneeling beside a shallow volcanic pool. The stone beneath your hand feels rough and warm. Water laps against mineral surfaces, while evaporation concentrates dissolved substances near the edges. The atmosphere smells sulfurous. Lightning flickers somewhere beyond dark clouds. If certain molecules are present, repeated wetting and drying could encourage reactions that are difficult in dilute, open water. Water is essential for life, but it can also interfere with some chemical assembly reactions. That is one reason origin of life researchers pay attention to environments where water comes and goes. A shallow pool can become concentrated as it dries. Rain or waves refill it. Then evaporation begins again, cycle after cycle. Chemistry receives another opportunity. Some hypotheses, therefore, place important prebiotic reactions on volcanic land, tidal flats, or other periodically wet surfaces. There is an obvious problem. How much exposed land existed on very early Earth? You encountered that uncertainty earlier. If the planet was dominated by ocean, with only scattered volcanic islands, suitable surface environments may have been limited. They were not necessarily absent. A small island can still contain thousands of pools elsewhere. Another candidate environment lies beneath the ocean. You descend through dark water toward fractured crust. Sunlight disappears above you. The water becomes colder, and pressure rises. Then faint mineral structures emerge from darkness. Hydrothermal fluids are circulating through hot rock. At some vents, heated water carries hydrogen, dissolved minerals, and other chemically useful substances into the ocean. Certain alkaline vent models are especially interesting. They produce natural gradients in acidity and chemistry across thin mineral barriers. Modern cells also exploit gradients across membranes. This resemblance has encouraged researchers to ask whether geological compartments could have helped early chemistry before biological membranes existed. The idea is elegant. It is not proven. Other scientists argue that deep ocean environments create serious difficulties for assembling key biological molecules. Without repeated drying, certain polymerization reactions become harder. Ultraviolet light, useful for some prebiotic pathways, cannot reach deep vents. The birthplace of life remains disputed. Perhaps there was no single birthplace. Different stages may have occurred in different environments, with molecules transported between them by water, wind, impacts, and geological circulation. Earth provides many laboratories simultaneously. Mineral surfaces offer another possibility. Certain clays can attract organic molecules and bring them into close proximity. Metal sulfide minerals can support chemical reactions. Tiny pores inside rocks create confined environments where substances become concentrated. Ice can even concentrate solutes between growing crystals under cold conditions. Nearly every proposed setting solves one problem and introduces another. That is why the question remains fascinating. You are not looking for one miraculous molecule that suddenly wakes up. You are looking for a sequence. Simple compounds must become more complex. Some structures must persist. Information must somehow be stored. Chemical reactions must acquire useful energy sources. Boundaries must separate an internal environment from the surrounding world. Eventually, a system must reproduce with variation. Only then can natural selection begin refining it. One famous experiment demonstrated how surprisingly far ordinary chemistry could travel. In 1953, Stanley Miller, working with Harold Urey, circulated gases through laboratory equipment designed to represent one possible early atmosphere. Electrical sparks supplied energy. After several days, the apparatus contained amino acids. The result became iconic. It showed that biologically relevant organic molecules could form under plausible, non-living conditions. But there was a catch. Scientists later concluded that Miller's chosen atmospheric mixture probably did not represent the entire early Earth particularly well. A strongly reducing atmosphere rich in methane and ammonia may have been less globally dominant than once assumed. The experiment was not useless. Quite the opposite. It demonstrated a principle. Given appropriate ingredients and energy, complex organic chemistry can emerge naturally. Later experiments using different gas mixtures, volcanic conditions, ultraviolet radiation, impact chemistry, and other environments produced additional pathways. The question shifted. Instead of asking whether nature can make organic molecules, researchers increasingly ask how those molecules became organized into evolving systems. Amino acids alone are not enough. You need something closer to information. Modern organisms store hereditary information mainly in DNA. But DNA is complicated. It depends on proteins and cellular machinery for replication and maintenance. Proteins themselves are produced using information encoded in nucleic acids. This creates an uncomfortable chicken and egg problem. Which came first? One influential answer is the RNA world hypothesis. RNA can store genetic information, somewhat like DNA. Certain RNA molecules can also catalyze chemical reactions, somewhat like protein enzymes. Perhaps early life relied heavily on RNA before the modern division of labor between DNA and proteins evolved. The discovery of catalytic RNA strengthened this idea considerably. Yet making RNA under realistic prebiotic conditions is difficult. Its components must form, concentrate, assemble, and persist. Researchers have developed increasingly plausible chemical pathways, but no complete historical reconstruction has been demonstrated. Scientists still disagree about whether RNA came first or emerged from an earlier chemical system. Perhaps simpler informational polymers preceded it. Perhaps metabolism-like reaction networks developed first. Perhaps both evolved together. The ancient Earth offers no preserved laboratory notebook. You return to the shoreline. Sunlight appears through thinning clouds. Ultraviolet radiation reaches the surface more strongly than it does under today's protective ozone layer. There is almost no atmospheric oxygen, so there is no substantial ozone shield comparable with the modern one. Ultraviolet light can destroy delicate molecules. It can also drive useful reactions. Once again, the same environmental feature can be obstacle and opportunity. Prebiotic chemistry lives inside these contradictions. Heat accelerates reactions, but can destroy products. Water enables molecular movement, but can break certain bonds. Ultraviolet radiation supplies energy, but damages complex molecules. Minerals can catalyze reactions while trapping products. Nothing is straightforward. Then there is the problem of concentration. An ocean is enormous. If useful molecules form only rarely, they may become hopelessly diluted. Small environments solve this more easily. Pores, pools, mineral surfaces, droplets, ice channels, and shorelines can gather molecules together. Lipids provide another intriguing mechanism. Some simple fatty molecules naturally assemble into tiny membrane-like structures when placed in water. They can form vesicles. These microscopic spheres resemble extremely primitive versions of cellular boundaries. They are not alive, but boundaries change chemistry. A molecule trapped inside a vesicle experiences a different environment from one drifting freely through the ocean. Useful compounds can remain together. Reaction products can accumulate. Internal chemistry becomes partly separated from the outside world. You have moved one conceptual step closer to a cell. Now imagine a vesicle containing molecules capable of imperfect self-copying. If some copies reproduce faster or survive longer than others, competition begins. Variation acquires consequences. Natural selection no longer requires a modern organism. It only requires heritable differences affecting persistence or reproduction. Exactly where chemistry crosses into biology becomes surprisingly difficult to define. Life is not one substance. It is an organized process. That ambiguity creates a scholarly puzzle. Researchers still debate which properties should define the earliest living systems. Must something possess a membrane? Must it reproduce independently? Does evolution matter more than metabolism? Viruses complicate definitions even today. The first life may have been stranger than any surviving organism. And there is another peculiar possibility. Perhaps the earliest successful living system was not the ancestor of modern life. Chemistry may have crossed the threshold several times. Some early lineages could have disappeared completely. All organisms alive today appear to share deep biochemical relationships, but that tells you about survivors. Evolution does not preserve defeated experiments merely for historical convenience. The true beginning could be lost. You watch waves entering shallow depressions along the ancient coast. Molecules move with them. Some attach to minerals. Others break apart. A few combine into larger structures. Most combinations accomplish nothing lasting. There is no intention. No molecule is trying to become alive. Across countless environments and immense spans of time. However, chemistry keeps experimenting simply because physical processes continue. Eventually, one network of reactions may become unusually persistent. A boundary may preserve it. A copying system may emerge. Errors may occur during replication. Those errors may become inheritance. At that moment, something profound changes. Chemistry has always responded to physical laws. Now a chemical system can also accumulate information from its own history. Successful variations persist. Unsuccessful ones disappear. Evolution can begin. You cannot yet identify the exact pool, vent, mineral pore, or shoreline where this transition happened. Perhaps nobody ever will, but Earth has supplied water, carbon, minerals, energy, cycles, gradients, and billions upon billions of molecular encounters. The silent planet is approaching its most consequential transformation. Soon, matter will not merely react. Some of it will begin to remember. Somewhere on the ancient Earth, chemistry crosses a boundary that nobody is present to witness. There is no flash across the sky. No wave suddenly turns green, and no first creature rises dramatically from a steaming pool. The transition from non-living chemistry to biology was almost certainly subtler than that. You would probably miss it. Imagine looking into warm water filled with minerals and microscopic chemical structures. Everything visible appears as lifeless as it did yesterday. Yet within that chemistry, something may now be copying itself. The copies are imperfect. That imperfection changes everything. A chemical system capable of reproducing with heritable variation can begin evolving through natural selection. Variants that persist or reproduce more effectively become more common. History enters chemistry. Before this threshold, a molecule simply existed until reactions altered or destroyed it. Now information about successful molecular arrangements can pass into future generations. Life has not merely appeared. Evolution has become possible. Exactly when this occurred remains one of Earth's greatest unanswered questions. The oldest widely discussed evidence for life reaches more than 3.5 billion years into the past. Some proposed biological signatures may be older. Claims approaching or exceeding 3.7 billion years have generated intense debate because ancient rocks can imitate biological patterns through non-living geological processes. The older the evidence, the harder interpretation becomes. Earth has heated it, compressed it, deformed it, chemically altered it. Then geologists arrive billions of years later and politely ask whether a microscopic feature once contained a living cell. The rocks are not always cooperative. You descend toward an ancient seafloor. Water above you is dark, while hydrothermal fluids move through fractured crust below. If early life emerged here, it may have relied on chemical energy rather than sunlight. Hydrogen produced through reactions between water and rock could support primitive metabolic pathways. Carbon dioxide provides carbon. Mineral surfaces offer catalytic possibilities. Some modern microorganisms survive through broadly comparable forms of chemical metabolism. That does not prove their ancestors originated at vents. Modern organisms have had billions of years to adapt. Still, deep environments provide an attractive feature: protection. The early surface receives strong ultraviolet radiation because there is no substantial ozone layer. Large impacts periodically disturb oceans and atmosphere. Life beneath water or inside crustal pores could be sheltered from some of these hazards. Now return to a sunlit volcanic shoreline. Here, different advantages appear. Ultraviolet light can drive useful prebiotic reactions. Wet and dry cycles concentrate molecules. Fresh volcanic minerals provide reactive surfaces. Pools can divide, evaporate, refill, and exchange material. The environment offers repeated chemical cycles. Which setting is correct? Scientists still argue. Some favor hydrothermal origins. Others favor surface pools. Additional models emphasize hot springs, mineral-rich sediments, ice, impact-generated environments, or combinations of several settings. The first life left no address. Even defining that first life creates trouble. Modern cells possess membranes, genetic information, proteins, complex metabolic networks, and molecular machinery refined through billions of years. The earliest evolving systems were almost certainly simpler. Perhaps RNA-like molecules copied themselves within primitive membranes. Perhaps metabolic reaction networks emerged before sophisticated genetic molecules. Maybe both developed together through gradual chemical evolution. There may never have been a clean dividing line. Consider a simple lipid vesicle. It forms spontaneously because certain molecules organize themselves in water. It is not alive. Now imagine that vesicle contains catalytic molecules, still perhaps not alive. Suppose those molecules help produce additional components, while the vesicle grows by absorbing material from its surroundings. Interesting. Then it divides. More interesting, if internal molecules are copied imperfectly and useful variations become inherited. You are approaching something increasingly difficult to call merely chemistry. The boundary becomes philosophical as well as scientific. Life may be a process rather than a switch. One particularly important concept is the last universal common ancestor, usually abbreviated in scientific discussions, though you can simply call it the shared ancestor of modern life. This organism was not necessarily the first living thing. It represents a population near the ancestral root shared by all currently known cellular life. By comparing genes and biochemical systems across modern organisms, researchers can infer some characteristics that ancient shared ancestors probably possessed. They used genetic information. They relied on proteins. They possessed sophisticated molecular machinery. They were already remarkably complex. That means the earliest stages lie even deeper. The shared ancestor of modern life had predecessors. Those predecessors had predecessors. Between prebiotic chemistry and the common ancestor lies an enormous hidden history. You are searching for a dawn after sunrise has already begun. There is a quirky clue inside every modern cell. Ribosomes, the molecular machines that build proteins, contain RNA at their functional heart. Proteins surround and assist them, but RNA performs central catalytic work. Some researchers view this as a molecular fossil from an earlier era when RNA played a larger role. Your own cells may therefore carry echoes of biology's ancient architecture. Nothing about that echo is visible when you look at yourself. Yet the machinery connecting genes to proteins may preserve a history older than animals, plants, continents, and perhaps recognizable oceans. Another clue comes from the genetic code. Almost all known organisms use closely related rules for translating genetic information into proteins. The shared pattern strongly supports common ancestry. A bacterium and a human appear radically different. At the molecular level, they speak variations of an ancient biochemical language. That discovery emerged slowly. For most human history, nobody knew cells existed. Ancient philosophers proposed many ideas about life's origins, including versions of spontaneous generation. Everyday observations seemed supportive. Maggots appeared on decaying food. Microorganisms emerged in stored liquids. Without microscopes, it was reasonable to imagine that life could arise routinely from non-living matter. Experiments eventually challenged this view. During the 17th century, Francesco Redi showed that maggots on meat came from flies rather than appearing spontaneously. Later investigations pushed the question toward microscopic life. In the 19th century, Louis Pasteur's carefully designed experiments demonstrated that microbial growth in nutrient broths came from contamination by existing microorganisms under ordinary conditions. Life today comes from life, but that does not solve the ancient problem. If life has not existed forever, then at some point, non-living chemistry must have produced systems capable of biological evolution. Pasteur addressed spontaneous generation under modern conditions. He did not recreate early Earth. The distinction matters. The modern environment is already occupied by organisms that consume organic material efficiently. Any fragile prebiotic system forming today would face immediate competition from 4 billion years of evolved biology. Early Earth had no such problem. The first successful replicators had the entire planet to themselves. They were not competing with trees, bacteria, fungi, or hungry graduate students. Only chemistry stood beside them. Once natural selection began, complexity could accumulate. A slightly more stable membrane might persist longer. A more efficient catalyst could accelerate useful reactions. A copying molecule with better fidelity might preserve information more reliably. Too much fidelity could also limit variation. Evolution works through trade-offs. Nothing needs to plan ahead. Small advantages become significant when multiplied across generations. Generations for primitive microscopic systems may be short. Geological time is long. That combination is powerful. You watch the ancient ocean for thousands of imagined years. Nothing changes visibly. Then you extend the view to millions. Chemical systems diversify. Some vanish, others spread. Perhaps several independent origins appear and disappear. We cannot know. Eventually, one lineage or community contributes descendants that survive. Their chemistry becomes increasingly organized. Membranes regulate internal conditions. Metabolic pathways capture energy. Genetic systems preserve information. Protein synthesis becomes sophisticated. Biology is now unmistakable. The planet has changed categories. There is another consequence you might overlook. Before life, Earth's chemistry responds to geology, sunlight, atmosphere, and impacts. After life, organisms become geological agents themselves. At first, their influence is microscopic. A cell absorbs molecules and releases waste. Multiply that process across oceans and millions of years, and planetary chemistry begins shifting. Life will eventually alter carbon cycles. It will affect minerals. It will transform the atmosphere. Much later, photosynthetic organisms will release oxygen on such an enormous scale that they change the chemical identity of the planet's surface. Earth and life will begin evolving together. You cannot separate them afterward. That partnership is still almost invisible here. The ocean remains dark. The shore remains barren. No animal moves. No plant catches sunlight. If you collected a cup of water, any organisms within it might be microscopic and simple. Yet the silence has ended in a way your ears cannot detect. Somewhere within that water, molecules are preserving information. Copies are being made. Variations are being tested by survival. The first enormous era of Earth's history is closing. The planet began as dust orbiting a newborn star. Gravity assembled it through collisions. A giant impact helped create its moon. Magma differentiated into core and mantle. Crust cooled. Rain fell. Oceans gathered. Chemistry became complex. And now, after hundreds of millions of years of planetary preparation, matter has begun doing something entirely new. It has started evolving. The ancient ocean still looks almost empty, but it is no longer lifeless. Microscopic organisms inhabit a world of dark water, volcanic islands, mineral-rich seafloors, and an atmosphere almost completely unsuitable for you. You cannot see most of them. A cup of seawater may contain the most advanced organization anywhere known in the universe at this moment. Yet to your naked eye, it appears ordinary. Life begins quietly. The earliest organisms were microbial, and their ecosystems remained microscopic for an almost unimaginable length of time. There were no fish moving through the water. There were no forests on land. No bird crossed the sky. The shore remained barren rock. Yet inside those primitive cells, natural selection was already exploring chemistry with extraordinary persistence. Organisms needed energy. Some probably obtained it from chemical reactions, involving compounds available in their environments. Others eventually developed ways of capturing sunlight. Photosynthesis would become one of the most important biological innovations in Earth's history. But photosynthesis is not one single process. Some early forms probably did not release oxygen. Organisms could use sunlight while drawing electrons from substances such as hydrogen sulfide rather than water. Then a lineage evolved something far more consequential. The ancestors of cyanobacteria developed oxygen-producing photosynthesis. They used sunlight to extract electrons from water. Oxygen appeared as a byproduct. To you, oxygen sounds wholesome. You associate it with forests, fresh air, and breathing deeply beside an open window. To much of the early biosphere, free oxygen was chemically aggressive waste. It reacted readily with surrounding materials. The planet had enormous capacity to absorb it. Dissolved iron in ancient oceans provided one major sink. When oxygen encountered iron, chemical reactions produced oxidized compounds that could precipitate from seawater. Layer after layer accumulated. Much later, these deposits became banded iron formations. You can still find them in ancient rocks. Their alternating iron-rich layers preserve a planetary chemical transformation. Imagine standing beside an ancient sea during part of this transition. Its chemistry is unlike modern seawater. Iron may be more abundant in oxygen-poor deep waters. Microbial communities thrive in environments that would seem alien to you. Near shallow illuminated regions, photosynthetic organisms release oxygen. Most disappears into chemical reactions. The atmosphere barely notices at first. Life keeps producing it. This continues for immense spans of time. Eventually, Earth's major chemical sinks become less capable of consuming every oxygen molecule immediately. Free oxygen begins accumulating more persistently. Around 2.4 billion years ago, atmospheric oxygen rose substantially during what scientists call the Great Oxidation Event. The name sounds sudden. It was not a single afternoon. Evidence indicates a complicated transition involving pulses, reversals, biological evolution, geological processes, and changes in atmospheric chemistry. Researchers continue debating the exact sequence. Why did oxygen rise when it did? The invention of oxygenic photosynthesis is obviously essential, but production alone is not enough. Oxygen can accumulate only when its sources exceed processes removing it. Volcanic gases consume oxygen. Reduced minerals consume oxygen. Organic carbon burial affects the balance. Changes in tectonics, nutrient supply, methane, and biological productivity may all contribute. Scientists disagree about their relative importance. Earth's atmosphere is becoming a ledger. Life writes entries on one side. Geology writes them on the other. The balance changes slowly. There is a curious consequence high above the surface. As atmospheric oxygen becomes more abundant, some oxygen molecules are transformed through photochemical reactions into ozone. An ozone layer begins developing. Ozone absorbs much harmful ultraviolet radiation. The same biological waste that disrupts many anaerobic ecosystems eventually helps shield surface environments from intense ultraviolet light. Pollution becomes protection. Earth enjoys complicated stories. The oxygen transition may also have influenced climate dramatically. Methane is a powerful greenhouse gas. On the early Earth, methane produced biologically and geologically may have contributed important warming under the fainter young sun. Increasing oxygen can reduce atmospheric methane through chemical reactions. If methane concentrations fell substantially, greenhouse warming could weaken. Earth experienced major glaciations around the broad era of oxygenation. Exactly how tightly these events were connected remains debated. You might therefore imagine a planet transformed simultaneously by microbes, atmospheric chemistry, and ice. Tiny organisms can influence global climate. That would have sounded absurd to almost every human observer before microbiology and geochemistry existed. Humans once explained the atmosphere mainly as an unchanging background. Modern Earth science reveals something more intimate. The atmosphere is partly biological. The oxygen you breathe exists at high concentration because generations of photosynthetic organisms continually altered planetary chemistry. The story begins mostly with microbes. Much later, algae and plants join them, but oxygen does not rise smoothly toward modern levels. For enormous stretches of the Proterozoic eon, atmospheric oxygen may remain considerably below today's concentration. Researchers debate the values intensely. Different chemical proxies sometimes suggest different histories. Earth may experience long plateaus, followed by later increases. Meanwhile, cells become more complicated. For perhaps billions of years, life is dominated by organisms without nuclei. Then eukaryotic cells appear. Your own cells belong to this category. They contain complex internal structures, including a nucleus that houses most genetic material. One of their greatest innovations comes through an extraordinary partnership. A cell engulfed a bacterium. Instead of digesting it, the two established a long-term relationship. The bacterium eventually became the ancestor of mitochondria. Mitochondria remain inside almost every cell in your body. They retain their own small genomes. You carry descendants of an ancient bacterial partnership wherever you go. Later, another endosymbiotic event involving cyanobacteria produced chloroplasts in the ancestors of plants and algae. Photosynthetic machinery became cellular cargo. Life began building complexity by combining lineages. The exact timing and sequence of early eukaryotic evolution remain uncertain. Fossils are sparse. Molecular clocks depend on assumptions. Chemical biomarkers can be difficult to interpret. Researchers continue debating when major eukaryotic groups diverged and how quickly complexity increased. Again, Earth's record becomes clearer only gradually, but the direction is unmistakable. Cells become capable of larger genomes, complex internal organization, and increasingly diverse forms. Some begin living in colonies. Multicellular organization appears in several lineages. A cell no longer needs to perform every task alone. Specialization becomes possible. One group can handle movement, another can process nutrients, another can participate in reproduction. The principle eventually produces bodies, before animals dominate oceans. However, Earth undergoes extraordinary climatic episodes. During the Cryogenian period, beginning more than 700 million years ago, glaciers may have reached tropical latitudes. The phrase snowball Earth is often used for the most extreme interpretation. You imagine oceans sealed beneath global ice. Reality may have included patches of open water or thinner ice, depending on the episode and model. Scientists still debate exactly how complete the freezing became. The evidence for severe global glaciation is strong. Glacial deposits appear in rocks formed near ancient tropical latitudes. Carbon isotope records reveal major disturbances. Climate models show how ice can reinforce cooling by reflecting sunlight. Once ice spreads far enough, its brightness sends more solar energy back into space. The planet can become trapped in deep cold. Volcanoes provide a possible escape, even beneath widespread ice. Volcanic activity continues releasing carbon dioxide. If weathering slows dramatically under frozen conditions, carbon dioxide can accumulate in the atmosphere. Eventually, greenhouse warming becomes powerful enough to melt ice. The transition out may be intense. Rain falls onto newly exposed rock. Weathering accelerates. Oceans receive large chemical inputs. Earth swings from extreme cold toward warmer conditions. Life survives. That persistence is remarkable. Microorganisms occupy refuges beneath ice, near hydrothermal systems, within sediments, and perhaps in open water regions. When environmental conditions improve, ecosystems expand again. Then, around 635 million years ago, the Ediacaran period begins. Larger organisms become increasingly visible in the fossil record. Some have soft, quilted bodies. Others possess shapes unlike most modern animals. Their relationships to later groups remain debated. For the first time, you can stand beside an ancient seafloor and imagine organisms visible without a microscope. The world is still quiet. There are no forests. Land remains mostly barren, though microbial communities may inhabit wet surfaces. Beneath shallow seas, however, life has begun becoming architectural. Bodies spread across sediments. Communities occupy the seafloor. Evolution has discovered size. Humans will understand this history only very recently. For centuries, fossils were mysterious objects embedded in stone. Some scholars correctly recognize them as remains of organisms, while others proposed different explanations. During the 17th and 18th centuries, careful anatomical comparisons strengthened their biological interpretation. Geology then revealed that fossil-bearing layers formed in sequences. Older strata generally lay beneath younger ones when undisturbed. Life had a history. In the 19th century, Darwin and Wallace provided a mechanism explaining how populations could change through natural selection. Fossils stopped being isolated curiosities. They became evidence of descent through deep time. Later genetics revealed relationships written inside living cells. Radiometric dating supplied numerical ages. Microscopes exposed microbial worlds. Satellites eventually allowed humans to observe Earth's atmosphere and biosphere as one interacting planetary system. The perspective widened again. You can now look backward and see what no ancient observer could have known. Earth is not merely a rocky planet upon which life happens to reside. Life has changed the planet itself. Microbes altered oceans. Photosynthesis transformed atmospheric chemistry. Biological activity influenced carbon cycling. Oxygen helped create ozone. Organisms affected sediments and minerals. Earth became a living planet through feedback between geology and biology. You stand beside the late Precambrian ocean. The air now contains more oxygen than the atmosphere of the earliest Earth, though still not necessarily modern levels. Waves move across microbial ecosystems and increasingly complex communities. The moon is farther away. The sun is brighter than during Earth's youth. Continents have grown and rearranged repeatedly. Almost 4 billion years have passed since the first crust cooled. Soon animals will diversify dramatically. Plants will eventually transform the land. Dinosaurs, mammals, and humans remain ahead. But the essential transformation has already occurred. The once sterile world of magma, steam, and bare rock now carries biology from ocean chemistry into the atmosphere itself. Earth is no longer merely habitable. It has been inhabited long enough for life to become part of the machinery of the planet. Thousands of years ago, another kind of observer looked upward. You stand beneath a clear night sky, with solid ground beneath your feet, an ocean somewhere beyond the darkness, and stars scattered across the heavens. Earth feels ancient. More importantly, it feels permanent. Mountains seem older than memory. Rivers follow familiar valleys, while the sun, moon, and stars provide the obvious movements of the natural world. Nobody can yet know that the ground itself travels. Nobody can measure Earth's age as 4.54 billion years. The story you have followed from cosmic dust to living oceans remains hidden inside ordinary stone. Humanity must learn how to read it. Ancient sky watchers begin with cycles. Babylonian observers record planetary motions and eclipses with remarkable persistence. Egyptian calendars connect celestial rhythms with seasons, agriculture, and the Nile. Greek thinkers increasingly use geometry to describe the heavens. Aristotle places a spherical Earth near the center of an ordered cosmos. Aristarchus proposes that Earth moves around the sun, although convincing evidence remains unavailable. Hipparchus measures stellar positions. Ptolemy later builds a sophisticated mathematical geocentric model capable of useful prediction. Earth remains central. It also remains essentially timeless. During the medieval period, astronomers across the Islamic world preserve, test, and extend earlier astronomical traditions. Measurements improve. Models are criticized. Observatories become increasingly ambitious. Humanity is learning that precise observation can challenge inherited assumptions. Then the transformation accelerates. Copernicus develops a heliocentric planetary system. Tycho Brahe gathers extraordinarily accurate naked-eye observations. Kepler discovers elliptical planetary orbits. Galileo points a telescope upward. Suddenly, the moon has mountains. Jupiter possesses moons of its own. Venus displays phases. The heavens look less like a separate realm and more like a collection of physical worlds. Newton connects them mathematically. The same gravitational framework that describes falling objects can explain planetary motion. Earth has been removed from the cosmic center, but its age remains mysterious. To discover that, humans must look downward. By the 18th century, natural philosophers and early geologists increasingly recognize that rocks preserve sequences of events. Sedimentary layers accumulate. Rivers erode valleys. Volcanoes build landscapes. Seas advance and retreat. These processes require time. James Hutton becomes one influential voice in this changing perspective. He studies geological relationships and argues that Earth's visible features reflect repeated cycles operating over immense durations. Later, Charles Lyell develops geological arguments, emphasizing processes observable in the present as keys to interpreting the past. Deep time enters human imagination. It is difficult to overstate how strange this idea becomes. A human lifetime feels substantial from inside it. Recorded history feels enormous. Geology reveals both as brief. Then fossils deepen the story further. Extinct organisms appear in ordered sequences through rock layers. Entire worlds existed before humanity. Darwin's theory of evolution by natural selection eventually provides a mechanism capable of producing biological diversity across vast spans of time. Earth now has both geological and biological history. Still, scientists cannot determine its absolute age reliably. Different methods produce conflicting estimates. One 19th-century approach treats Earth as a body cooling from an initially molten state. William Thomson, later known as Lord Kelvin, calculates ages far shorter than modern estimates. His physics is serious. His Earth model is incomplete. He does not know about radioactivity, and internal heat transport is more complicated than simple conduction. Then atoms reveal another clock. At the end of the 19th century, scientists discover radioactivity. Ernest Rutherford and others recognize its implications for geological dating. Radioactive isotopes decay at measurable rates. Minerals can preserve parent and daughter isotopes. Time has become measurable inside matter. During the 20th century, radiometric dating transforms geology. In 1956, Claire Patterson publishes an age of roughly 4.55 billion years, based largely on lead isotopes in meteorites. Modern measurements refine the estimate. Earth is about 4.54 billion years old. The number finally connects your journey. The ancient zircons, the differentiated core, the moon-forming collision, the cooling crust, the first oceans, all belong within a measurable chronology. Then humanity leaves Earth. Spaceflight turns planets from wandering lights into landscapes. In 1957, Sputnik becomes the first artificial satellite to orbit Earth. In 1961, Yuri Gagarin becomes the first human to orbit the planet. Then, in December 1968, Apollo 8 carries Frank Borman, Jim Lovell, and William Anders around the Moon. From lunar distance, the astronauts see Earth suspended in darkness. Anders photographs it rising above the Moon's horizon. The image becomes known as Earthrise. For the first time, millions of people can contemplate their world from somewhere else. The planet appears small. Blue oceans dominate its visible surface. White clouds swirl above them, while continents occupy portions of the illuminated disk. No borders are visible. Neither is geological time. Yet everything you have followed is contained inside that tiny sphere. The core lies hidden beneath it. Ancient zircons survive within its crust. Life fills its oceans and atmosphere. The moon-forming collision is written into the companion from which the photograph was taken. Humanity has finally stepped far enough away to see home as a planet. Other instruments continue widening the perspective. Spectroscopy reveals the chemistry of stars. Radio telescopes expose an invisible universe. Photography allows astronomers to accumulate faint light over long exposures. Space telescopes rise above Earth's atmosphere. Modern observatories study planets forming around distant stars. Astronomers discover thousands of exoplanets. Some are rocky. Some orbit within regions where temperatures could permit liquid water under suitable atmospheric conditions. Earth is no longer the only known planet, but it remains the only world currently known to contain life. That fact changes the ancient question. For thousands of years, humans asked what the heavens were. Now you can ask whether another Earth exists. Modern planetary science approaches that question by studying the same processes you have encountered here. How do rocky planets form? How do they acquire water? How do atmospheres survive? What produces long-term climate stability? Does plate tectonics matter for habitability? How often does chemistry cross into biology? One example. One is not enough to establish universal rules. Mars demonstrates how differently a neighboring rocky world can evolve. Ancient Mars possessed rivers, lakes, and perhaps substantial bodies of water. Today, its surface is cold and dry beneath a thin atmosphere. Venus offers another warning against simplicity. It is similar to Earth in size, yet its surface is extraordinarily hot beneath a dense carbon dioxide atmosphere. 3 nearby rocky planets followed dramatically different paths. Why Earth remained habitable for billions of years is still being investigated. Perhaps there was no single reason. Its mass mattered. Its distance from the Sun mattered. Water mattered. Atmospheric evolution mattered. Geological recycling probably mattered. The moon may have influenced aspects of its rotational history. Life itself eventually became part of the climate and chemical system. Habitability is a relationship among processes. The story is not finished. Earth's future will remain dynamic. Continents will continue moving. The Atlantic will not remain unchanged forever. New mountain ranges will rise as others erode away. The moon will continue receding, while Earth's rotation changes gradually. The sun will also evolve. Its luminosity increases slowly as hydrogen is converted into helium in its core. Over immense future timescales, that brightening will alter Earth's climate, long before the sun becomes a red giant. Increasing solar energy is expected to make Earth's surface progressively less hospitable. Eventually, oceans may disappear. The planet that spent its youth acquiring water will not keep those oceans forever. Several billion years from now, the sun will leave its present main sequence stage and expand dramatically. Earth's exact fate during the red giant phase depends on complex interactions, including solar mass loss and tidal effects. It may be engulfed. Even if it escapes direct engulfment, the familiar living world will already be gone. The mountains, oceans, forests, and cities you know are temporary arrangements of ancient matter. But temporary does not mean insignificant. You stand beneath the night sky again. Now the darkness looks different. You know the iron beneath your feet descended toward Earth's center when the planet was young. You know the moon above you probably formed from a planetary collision. You know ocean water contains atoms with histories extending beyond Earth itself. And you know the observer looking upward is part of the same story. Humanity once placed Earth at the center of the cosmos. Then observation moved it outward. Earth became a planet around the sun. The sun became one star within the Milky Way. The Milky Way became one galaxy among an enormous population. Yet this shrinking of Earth's cosmic importance produced another realization. The universe became aware of itself here. At least once, atoms forged through cosmic history became oceans, rocks, microbes, animals, nervous systems, telescopes, laboratories, and questions. You are not standing outside Earth's history and examining it. You are one of its recent consequences. And now, the long journey can become quiet. The molten surface has cooled. The ancient rain has passed into oceans. The first dark crust lies beneath continents built and rebuilt beyond counting. Above them, the moon moves silently through reflected sunlight. You can imagine the planet turning beneath you, carrying water, stone, life, and memory through darkness. There is nothing more you need to follow tonight. Earth continues onward. The stars remain above you, and for a little while, everything is still enough to rest.